All right. View dashboard. Okay. So it looks like I'm online. I know there's been a few little glitches in getting this live streaming operation working. So hopefully when I'm doing this project live, there won't be too many things disrupting it that make it kind of annoying or difficult to see what's going on. But basically, let me just explain what I'm doing here and what I'm trying to do. So some of you may remember I did a project almost 8 years ago now called the MIT Challenge. And the idea at the time was that MIT, graciously enough, puts a lot of their class material online for free. So if you want to learn from one of the best schools in the world on all sorts of topics, but particularly STEM subjects, science, technology, engineering, math, things like computer science, things like physics, things like higher mathematics, MIT classes are one of the best and most challenging and rigorous resources. And this was true back 8 years ago, and I believe it is still true today, that they offer some of the best resources for learning these higher mathematics at a higher level. I think if you want to do high school or maybe even just sort of intro college courses, there are better resources that are a little bit more tuned to beginners. But if you're willing to challenge yourself and try to take on some of the harder classes, MIT is a good place to really test your mettle. Now, I worked on this project about 8 years ago, and I've also done other projects since. So I worked on a project called The Year Without English, where I went with my friend Vat, and we went traveling to 4 different countries to learn languages. And I even did a short project called Portrait Drawing Challenge, which for 30 days I worked on drawing portraits. And in each of these challenges, one of the things that I struggled with is what I'm going to call the documentation problem, which is that I'm doing something that's intense and it takes up a lot of time, and it can often be kind of stressful and require a lot of focus. But at the same time, I have to also be aware that people are going to be looking at it after. So I have to be really good about documenting what I'm doing, how I'm doing it. And there's also the challenge there that you want to try to be as honest as possible. So if I was saying, oh, I was working 60 hours a week, I don't really want to be saying that if I was only working 35 hours a week. Or if I was saying in The Year Without English that we weren't speaking any English except for these like small little exceptions, I want to be really clear what those exceptions were. One of them, for instance, was talking to my parents back home over the phone. But the situation is difficult because when you are doing the project, it's also difficult to simultaneously document it. And nowhere was that more clear when doing the big projects like the MIT Challenge or The Year Without English. The Year Without English, for instance, we made these kind of mini documentary videos. And so often we'd have to take breaks from our language learning to like, okay, pull out the camera and try to record some progress and do this kind of thing. And so recently I've seen a lot of people doing live streaming, in particular people who, in this case, doing video game streaming, who are doing difficult cognitive challenges, that they're doing something that is mentally difficult, that requires a lot of focus, but they're doing the entire process live on camera. And that just seemed ingenious to me because this didn't exist when I was doing the MIT Challenge, but it's something that can solve a lot of problems with doing this process. So you can solve a lot of problems with documenting things if you have it all on live stream. So if I were able to go back in time and have that technology when I was doing the MIT Challenge and I just live streamed the whole thing, it would be a lot clearer what I did, exactly how I was doing it. And, you know, although I don't think everyone is going to want to watch the thousands of hours that probably would have represented live on camera, it does give you a chance to really see what it is like that I'm doing, and also participate if you want to comment on it or ask why I'm doing something or see these kinds of things. And so for this, I wanted to try to get more comfortable doing a live stream type project. And so I wanted to pick something that I was familiar enough with how it works to know that there weren't going to be any major obstacles for doing it live streamed, but at the same time would be challenging enough and interesting enough that I could actually try to do something that was going to be difficult. Obviously, if I do a class that I'm going to find really easy, then there's not that much to doing the project. And so I wanted to do a project that when I think about it, I'm like, oh man, that sounds really difficult, or I had some experience and I'm like, ooh, I don't know how I'm going to do that, because then that's exactly the situation that I want to try to show you guys, is not to show you something where I'm breezing through it because I just already know a lot of it and it's super easy, but something that, kind of challenges me. And so that brings me to this project, which I'm calling Let's Learn Quantum Mechanics. So I'm just trying to set this up here to see if there's any way I can look at the chat, because it looks like my I think live control room, maybe I can do it from here. Unfortunately, the application I'm using to stream it, called Lightstream, Go Lightstream, has not loaded the chat window for me. So I'm hoping I can just get to a page here where I can load it. I'm hoping that I can figure out this software so that when I'm doing it here, no. Oh, okay, here we go. Oh, cool. So I've got a few people watching me already. Wow, okay. So, all right, I will try to have the chat open. I can't promise I'm going to be super interactive in the chat. That was one thing I was a little worried about, because like in theory, doing a hard class, you can't be like chatting with people at the same time. You have to actually be focused on it. So I am going to say that if we're talking about the class and the things that I'm doing in the class, and particularly the things I'm doing right now, I'm going to be more responsive, I'm hoping, with chatting. Whereas if you just want to ask questions about me or about my life or these kind of things, I might try to save a little bit of time at the end of each day to just kind of have a debriefing and like free chat where I'm not focused on something. So I don't want to be rude. I don't want to not talk to people while I'm doing this. I know that interaction with the person while they're live streaming is a big part of what live streaming is, but I'm also aware of the complication that if I'm, chatting to people about my, my day-to-day life or what I did on the weekend, I'm not going to get a lot of hard physics problems done. So I got to kind of make that trade-off. So just to go back, what am I doing here? So I call this project Let's Learn Quantum Mechanics, a little bit of a play on the idea. There's this popular video game streaming format called Let's Play, where people will like play a video game. And I thought, what if you did that for learning something? What if you did it where, I'm going to just start this. I'm not an expert. I'm not teaching the class. This isn't something that I've already mastered and I've come here to show off all these insights. But I want to show you the process of me going through it and being like, whoa, okay, I have no idea how to do that, to trying to troubleshoot, to solve those problems, to see if I can learn it. So over the next month, I'm going to be trying to do this project. It's going to be about 6 hours a day, Monday to Friday. So my plan is tentatively about 8 a.m., which is right now, it's 8 a.m. So I started a little bit early because I was having some technical problems. But it's about 8 a.m. Till 11 a.m. Pacific time. I'm located in Vancouver, Canada, so I'm on Pacific time, and 8 a.m. to 11 a.m. in the morning, and then I'm hoping 2 p.m. till 5 p.m. in the afternoon as the core hours for working on the project. I do have other work that I have to do beyond this. It's not that this is my entire life and all I do is live streaming. I have a business with employees and I have articles to write and a book to publish and meetings and calls and all these kinds of things I'm going to take. So I've tried to clear enough space so that I'm not going to be bogged down with other work while I'm working on this. But I also wanted to leave myself a gap in the middle because I'm sure there's going to be a lot of work that's going to come up that I'm going to have to handle. But that's also partially what I wanted to talk about too, is that this is sort of a part-time project. It's not full-time in the sense that, the MIT challenge was definitely full-time. I was working on that, Monday to Friday. I wasn't working on anything other than the project. So I wanted to show kind of how you could also plan this if you have a job or other commitments and you're also learning something that, you can't put everything in life on hold while you're doing it. And the reason I picked this quantum mechanics class was for a few reasons. So one of them was that I had done some physics classes in the MIT challenge. So this was, again, about 8 years ago. I did 801, which was the classical mechanics, which kind of talks about Newtonian mechanics and gravity and pendulums and these kinds of things. And then I did 802, which was electromagnetism, which was talking about Maxwell's equations. So you have things like voltage and magnetism and these kinds of things. And this was all I went to in the MIT challenge. It was the MIT challenge was focused on computer science. And although the way they teach it in MIT is that computer science and electrical engineering are the same degree program, you can concentrate in one or the other, but everyone who's doing computer science also has to learn some electrical engineering and vice versa. Because of this, I did do those physics classes, but I didn't go further than that. So I never learned special relativity. I never learned general relativity. I never learned quantum mechanics. I didn't go beyond that. And quantum mechanics was something that had always really interested me. It was something that I had, when I was a teenager, there were popular books on physics, and I always just liked reading them because they're just so mind-blowing. Just the ideas that, the world that we live in is based on these quantum rules, which are just so bizarre and so different from our ordinary way of thinking about things. Like this whole idea that if you measure something, it's going to change its behavior in ways that just seem unpredictable, or the idea that photons and protons and electrons are made up of waves. They're not just a static kind of little particle, makes it very difficult to wrap your head around, like, what's going on here. And the thing that I realized after reading a lot of these popular accounts is that a lot of the confusion comes from the fact that I'm not doing the math. That when I read these popular accounts, they're ignoring all of the math behind quantum physics. And in some ways, the intuition of quantum mechanics is the math, that it is being able to understand what is the mathematical structure. And if you ignore all that and you just rely on familiar analogies, so you just rely on your intuition with everyday objects, you get all these confusing paradoxes. And I know from interacting with people who have understood physics and understood quantum mechanics particularly, that even though it's confusing and there's still unresolved issues with interpretation, actually using quantum mechanics to make predictions to understand how things behave and why they behave the way they do is quite straightforward. And it's in fact one of our most successful physical theories, one of our most successful theories about how the world works. And so I wanted to take this opportunity to learn in a little bit more depth something that had always fascinated me when I was younger, to really go into how does quantum mechanics work? What is it? What are the math behind it? What is the actual process? And my starting point for this was to go back to how I did the MIT challenge, see if there's some good MIT classes and take them. Now, this was about a year ago, and I found this series of lectures from 804 Quantum Physics 1, which is the intro class to quantum mechanics for MIT. There's more classes than this, so this isn't like I'm going to be covering everything there is to do with quantum mechanics. And I started watching the lectures, and they were really good. So I've watched some of the lectures already. It's not to say that I've had zero exposure to this class. But I was watching these lectures, and when the math break would happen and they started doing the math, it would immediately, okay, all right, this is over my head now. I'm not following what's going on. And I recognize, you know what, it's not enough to watch the lectures. I know I talk about this a lot, that you have to do problems, you have to do practice, you can't just watch things. But this was definitely true in this class, that just watching it, I'm not going to get the math by just watching it. I actually have to focus and do these problems and really work through it myself. And so, that's kind of a difficult process. It's not something I don't just whip out quantum physics problems for fun to do in my spare time. So I thought it would be cool to do a kind of ultra learning project to tackle this, where I'm actually going to focus on it, actually going to do the problems. So basically, this next month is going to be me trying to do this class on live stream. There's going to be some complications because I don't have all the prerequisite classes. In particular, I'm missing 803 waves. So I did 801 and I did 802. I didn't do 803, and now I'm doing 804. So I'm missing one of the key components to how this class works. I don't know how it's going to be. It might be difficult. I might have to go back and learn potentially even an entire other class in the process of learning this one. Not to mention the fact that a lot of the stuff that I would need, so differential equations, linear algebra, physics, all of these subjects, I did do them in the MIT challenge, but that was almost 8 years ago. And I do think that I learned them when I did them then, but at the same time, if you were to, be in a similar situation where maybe you're like me and you're in your early 30s and you're going back to math classes you did in your early 20s, there's going to be a difference. There's going to be some relearning. There's going to be some, oh, right, how was I supposed to do this? And so part of me was also wanting to do this because I wanted to talk about that process of relearning. I still have all my old notebooks from the MIT challenge, so maybe I'll be busting a few of them open. I still have some of the textbooks sitting on my shelf. So maybe it's going to be the case that, oh, you know what? I completely forget some of these concepts from linear algebra. I completely forget some of these concepts from differential equations. And so I'm going to have to be going back and relearning them. So one of the reasons for taking this is just that it is a bit of a class that is a little bit above the level that I should be taking. If I were really trying to take this in the smooth and steady approach, I would take 803 first. I would do all those problem sets. I would really master that material. I'd go back. I'd relearn all those things. And then, well, I would start 804. So this is going to be a process of me kind of like trying to live on camera show how I approach studying, how I approach learning things. And it's also going to hopefully be a process that, maybe you can engage in if you're interested in learning quantum mechanics. I'm going to be playing the lectures on the stream. I'm going to be working out the problems. I'm going to be trying to speak out loud of my own thinking of how to solve them. I'm going to be trying to do, if I do Feynman techniques or I do any of these sort of explanation processes, I'm hoping that this can be sort of interactive and engaging and not just, a month of me dryly writing notes on a piece of paper, but also something where we can interact and hopefully learn together some of these subjects. Because my end goal of this is not really to be really good at the equations, although I think being good at the equations is how I'm going to get the intuition. But my goal is not to proceed and become a physicist and have to work with these equations all the time to get practical results for my career. Instead, what I'm hoping to do is get my head around the intuition behind the math so that if I wanted to learn anything that requires quantum mechanics, or I want to even just understand those popular books that I read when I was a teenager, I have an intuition for how it works. And I understand why it works that way rather than just some kind of heady, oh, it's sort of this, it's sort of that kind of analogy. So I haven't done that much preparation. I did download some of the material just so you wouldn't have to be waiting for me to be downloading these videos from MIT or having lag or streaming. So I did do some of that. I have watched, again, as I said, some of these lectures about a year ago. So it does mean when I'm watching them, I'm going to be watching some of them for the second time as opposed to just watching them all from scratch. But I haven't done any problems yet. I haven't really looked at any of the problem sets, any of the materials. I haven't really done that much preparation. I haven't scheduled things out. So normally when I start a project like this, before I officially begin, I start looking at, okay, what's the material? What's going to be the sequence? What's going to be the plan for actually tackling that? And I thought that was an important part of the learning process. So I figured, let's do it live on camera rather than come in with like, well, I've got all this plan and this is my schedule, and this is my calendar. I'm going to just work it out here on paper. And then you'll also see when I make mistakes. So if I do a schedule and then I decide halfway now, this isn't the right way to do it, then you'll also see how there's kind of some flexibility and feedback in this process. So I'm going to be beginning in, in a few minutes. I'll start working on that. And I know that there is, in fact, actually some people watching me do this project right now. So if you are on the chat right now, why don't you ask me any questions that you have about this project or anything that you'd like me to address before I get started, because it'd be good to have it on the record here for the video of what I'm trying to do. And maybe there's something I missed that would make sense for that. So I'm trying to do the chat. I do believe there is some kind of delay here in the chat. So I think it's about a minute or two difference between when I'm saying things and when stuff is happening in the chat. So it might be a little bit delayed, but let's see what, looks like we have 25 people watching. So this is going to be interesting. So Tuning BG says, what's the goal of the project? So the goal of the project very simply is on a basic level is to learn the basics of quantum mechanics and have an intuition about the formulas. Now, in order to formalize that, because that's kind of a vague notion, what I'm doing is I'm doing an MIT class. Very similar to the MIT challenge, I'm going to learn the material of the class and try to do the final exam. Obviously, doing a final exam, which involves a lot of equations and problem solving, isn't exactly my goal, which is having this sort of intuitive understanding. But in some ways, it's a harder goal, because in order to actually solve the problems, you not only have to have the intuition, you also have to be able to do the math. I do have some experience doing MIT classes. They're not the kind of problems that you can just memorize solutions to. So in most of the classes I've studied before, it's not like you could get through an exam without understanding the subject, because the questions they're going to ask you are all different. There are sometimes going to be ones that, okay, I saw something similar to this in a practice problem, so maybe I have memorized how to solve it. But for the most part, they're not like this. They could be asking any question, any way of using the math. And that's one of the reasons I like the MIT classes, is because they do really test your intuition. If you really understand them and you have the math abilities to back them up, you can go through them. So my idea is to just do that. I'm going to do this class, watch the lectures, do a bunch of assignments, try to explain the concepts to you, try to explain the concepts to myself about how the math works. And then hopefully at the end of the project, I'm going to do this final exam and it'll go well. I did have to download the final exam from a different session of the class. I don't think that's going to be a problem for this one, but I have taken MIT classes where if you do a different session, they have different things that they covered, and then it's impossible to do the exam. An example of that from the MIT challenge was chemistry, where I did the chemistry class, and then I had to get an exam from a class that was not the one that I learned from, and they covered different concepts. And so when I was doing the final exam, I was like, oh, this doesn't work. I can't do this exam. This is a bunch of concepts I haven't learned. And so I had to go off of the midterms from the actual class, because there wasn't a final exam for that one. So I'm hoping that this isn't going to be the case, that I start doing the final exam and I'm like, oh, no, this is not the material we covered. But at the same time, I have a lot of problem sets. I have a lot of evaluative things. So even if the final exam thing doesn't work out the way I'm hoping it will, I'm still going to have a lot of material to test whether or not I know what's going on with quantum mechanics. So, someone is asking me what books I bought for the project. So I only bought one book, and this is, again, not the book that they recommend for taking. They recommended 4 textbooks for this. It's just to let you know, this is going to be the 804, I believe it is the 2013 spring session. So if you go to MIT OpenCourseWare, so I think it's ocw.mit.edu, and you look for 804 2013 spring, that's the class materials that I'm going on as a reference point. There is another class that has lecture videos, but I liked this instructor the most, so that's why I'm going with him. And then for books, I do have this book here. This is an Intro to Quantum Physics by A.P. French and Edwin F. Taylor. And this is an MIT book even. I got this one because this one was recommended in a different session of this class, a more recent session. They recommended this book. The other textbooks that were recommended, I tried buying one of them on Amazon. They're all like out of print, and so I was getting them from secondhand sellers. I waited a month for it to get delivered. It never showed up. So I just had to say, you know what, I just got to get a different one. And this one was available on Prime, so I got it. I don't think I'm going to need the textbook too much. It's mostly a backup explanation if I didn't understand the explanation in the class, because the material is actually quite good for this one. So when I was doing the MIT challenge, often there were no lecture videos. So if I didn't have a textbook, I had no way of really learning the content. But this is not like that. There's tons of material. There's even an entire second class with more lecture videos on it. So I don't think that there's going to be a dearth of materials for doing this class. So yes, all the resources except for this textbook are going to be online and open source. So as I said, if I'm going to be using this textbook, I will put it under the camera. So if it's, I do have a camera that's down here. I'll just see if I can just do a quick switch here to, so when I'm doing notes, I will be here. And if I want, I can have my textbook, and you know, we can learn together. So if I'm using it, I'm going to have the books here. However, I don't think I'm going to be doing that much from the books. I think it's going to mostly be the lecture videos and the resources that MIT provides for free. So we'll just sort of see how it goes. It may be the case that there's some tricky problems that, like, the explanation they gave in the lectures wasn't enough. the assignments wasn't enough. I have to go back and I have to really study it. And there's probably going to be stuff that I'm going to go back to my old classes. So classes that I took 10 years ago. I think my feeling right now is that linear algebra, I understand at a conceptual level, but I think a lot of my practice for doing linear algebra is going to be a little weak. I haven't done it in a while, so I might have to go back and refresh myself on some of those algorithms, procedures. And differential equations is going to be hard. I do sort of remember differential equations. I have the big level picture of what differential equations are and how they work. But again, a lot of the details for how to solve very specific problems I may not recognize in the MIT class for 804. So I think what I'm going to do is just take the class, and if it looks like, oh, what are they doing here? I don't understand why they're doing it. And I recognize that it's differential equations, or recognize that it might even be from the class that I didn't take, this 803 waves. So that's also on MIT. And so I might be able to go back and do that. Ashwatosh is saying differential is very easy. Well, you know what? Ease is really something that's relative, because I think if you have something that is challenging for you, it could be really elementary for someone else. And one of the things that I like to talk about when I talk about learning is that difficulty and ease are very much based on what you've learned in the past. So if I've learned this, quantum mechanics, if I've learned this in the past, then doing this class is super easy because I've practiced all the skills, I've practiced all the concepts. So my goal for this project wasn't to show off how smart I was or how to look at me, I know all these things. My goal for this project was, this is going to be hard for me. And because it's hard for me, I want to show how you can tackle projects or classes that are hard for you. So quantum mechanics may be way over your head. If you haven't done any math, this might be way too hard for you. Or you might be an engineering student, a physics student, for which doing this class is actually way too easy for you. And so you're going to be seeing me struggle with stuff that you know the answer to, like this. And so there's really no way around it. I can't be, at the same time showing off how good I am at knowing everything. My process is just, here's something that's hard for me, and here's how I'm going to learn it. So I'll give a last chance to ask any questions about the project, and then I'm going to just get going with trying to plan it out. So Abhishek Kumar says, what to do when resources won't feel enough? Well, we'll find out. We'll find out when we do this, whether these resources are enough. If they're not, I'm going to look for new ones. Another book by David J. Griffiths, Morton M. L. Hansen says, their book by David J. Griffiths. This is also good. This textbook was not chosen because I thought it was the best. I chose it because I could get it delivered here in 2 days when the textbook for the class did not show up after a month. So this is me playing around with this. I'm not saying that I have exactly the right books here. Again, the resources for MIT are pretty thorough here, so the textbook's more of a backup than my main thing. What do I have? So Tony VG says, why did I choose exactly quantum mechanics? So as I said, one of the reasons is that quantum mechanics is kind of a famously hard subject. It's one that I was always really interested in. I always found these, the particle wave duality, the double slit problem. I've read books that have talked about this in a non-mathematical way. So I've read books like Brian Greene's The Elegant Universe or Stephen Hawking's A Brief History of Time, and they are always just sort of like this is just so crazy that the world actually works this way. But they're also something that if you don't understand the math, it's really hard to have an intuition about, because you have all these analogies from your regular life, but you don't have the actual patterns that are actually in play here. You're just cobbling together analogies that don't really work that well. So that's one of the reasons, is that I wanted to develop an intuition for the math, for what's actually going on, so that when I read problems about physics or biology or chemistry, or let's say I want to take a quantum computing class, I want to go back to the MIT challenge topics and learn about quantum computing. I want to be able to get what's happening there. I don't want it to just be some really weird, okay, I guess I just have to memorize this because it doesn't make any sense to me. So that's one reason to do quantum mechanics. The other reason is that the class is kind of the right difficulty level I wanted to do live on camera. So if I pick a class, like one idea I had was doing machine learning, and I think unless I'm doing something kind of advanced in machine learning, I think I have a little bit too much computer science background knowledge for that to be necessarily a challenging class. If I'm doing something hard, like I'm doing a lot of convolutional neural nets or things that are not your intro level stuff, maybe. But if I'm doing like what I'm doing here, where I'm just doing an MIT class, I don't know whether I'm going to be able to find something that's the right level of difficulty. It might either be too easy because I've done too much background stuff. This, on the other hand, is going to be hard. I'm missing one of the classes. The classes that I did have from the MIT Challenge, I did about 8 years ago. So I'm going to have to relearn a bunch of stuff. I'm going to be honest with you guys here right now. I have not done math problems like this for probably 7 years. So again, when I have to do, even simple stuff and probably even algebra, maybe there's going to be some things that I make silly mistakes on, just because, it's like any other skill that you've done. If you haven't done it, if you haven't spoken a language for 8 years, you're going to be stammering a little bit when you're doing it. So I haven't spoken the language of higher mathematics for a long time. And so I'm going to have to go and practice that. So part of the reason for doing this was that I felt this class was difficult enough to justify doing this kind of project. So Justin Fulkerson is saying, I don't think you can self-learn quantum, in my opinion, lol. So you know what, Justin, I got to be honest with you. I'm not actually self-learning this. I have the entire resources of the MIT class at my disposal. So this is a little bit of a misnomer almost, that when I am doing MIT classes, I am self-educating, because really I have almost the same stuff that an MIT student would do. In some ways, I'm actually at an advantage because I have all the material up front. Now, I don't have feedback from a teacher, but from doing the MIT Challenge, I feel like that is only a problem in about maybe 5% of cases, because usually there's a way to solve the problem yourself. It's only really when, you know what, I really don't get this, I really need the explanation, someone needs to explain it to me in a different way, and I need to get this exact thing, that sometimes you need some help. But even then, I'm doing this live stream. I'm sure there's going to be some people on the stream who maybe know what I'm going through, and maybe people are going to pitch in. So Toonie VJ is saying, how can we follow you? What advice would you give for us to participate? So there's two ways you can participate. So one is you can just watch. I know lots of people watch video game streamers. People watch streamers doing various things. I have no idea whether watching a stream of me studying is going to be entertaining enough to have people watch me. But I mean, I'm also kind of doing this so that there'll be a video later if I wanted to clip out, okay, this is how you approach a certain studying technique. So I don't know whether that's going to be interesting enough for you, but I'm hoping that I can be engaging and try to make the material interesting, because it's interesting for me. So this is, I love learning these classes. I love doing the MIT classes. So I'm hoping that that passion will come through a little bit on the camera. And the other way is that you can learn the class with me. So I don't know that you've had the prerequisites. As I said, I'm missing some of the prerequisites. You may be missing more. So if you have not done quantum physics, if you have not done any of these things before, it might be challenging for you too, and so I can't guarantee that you are at the position that I'm at in doing this class. However, I'm going to try to do it a little bit Feynman technique style, where when I learn something, I'm going to try to talk as much as I can about what I'm learning. I'm not going to just try to keep it in my head. I'm going to try to say, okay, when I'm solving a problem, what's going on in this problem here? So I'm hoping that that's going to bridge the gap a little bit. But obviously, if you haven't taken high school algebra, this is going to be a difficult class, because there's a lot of math and it's hard and it's advanced math. But if you want to join me with the class, this is more than welcome. I'd love to have some people who are taking it along with me. Some other topics. If you have any off-topic questions, now is the time to ask, because I'm probably going to be ignoring off-topic questions while I'm actually studying, because I'll find them distracting. So now's a good time to ask. So Felipe Tremblay says, did you make those paintings on the wall? I did. I was setting up this room, and I actually have, like, if I turn the camera here, an open kind of window there. And I didn't want to have just sort of my kitchen kind of visible from the background. So I wanted it to be into this corner. And then there was a big white wall here where I needed something. So I just put up a few of my paintings. So we'll see. These are just a few still lifes I did a while ago. So does anyone have any last questions, or should I get started with stuff? So someone's saying, would you show all the memory tools you use during your studies? Yes. It's not going to be so much memory tools. Physics classes don't require that much memorization. I'm not really going to be memorizing the equations, let's say. I think that there is a formula sheet for the final exam. So even if I needed it in a blind situation, it's not going to be a problem. I don't really, like, I'm probably going to learn these things as I go. So I don't think it's going to be the case that I'll have no intuition of what the equations look like, but it's not really going to be so much memory. It's going to be a lot more getting an intuition and understanding. And in some ways that is a memorization task because you're learning a lot of discrete facts and discrete ideas. But another way, it's also an integration. So one of the popular ideas I've talked about years ago was holistic learning, which is where you take abstract concepts and you link them to things you understand. So you cobble together your understanding out of analogies, out of pieces of information, and do things like the Feynman technique, do things like, great diagrams, create mental images. So I'm going to be trying to do that. I'm going to try to show as much as I can of what I'm doing. But there's probably going to be a lot of stuff that I don't even think of as a studying technique. I just think of it as this is how you take a class that is going to come here. Like, what do you do when the materials aren't sufficient? Or what do you do when you don't understand something? Or what do you do when, all right, it's clear that I have not practiced my algebra enough, or I haven't practiced my my thing enough here. So yeah, there's going to be a lot of stuff for that. So I think now at 8:30 I should probably move on to starting the actual project. My plan right now, as I said at the beginning, was to go from 8 a.m. Pacific time till 11 a.m. Pacific time, and then again from 2 p.m. till 5 p.m. So it's about 6 hours a day. I need to leave myself a chunk in the middle to catch up on work and stuff. And I'm probably going to be doing it 5 days a week. Now, I don't know how far it's going to go. I don't know how long it's going to take me. My hope is that if it looks like I can pass the exam a little earlier, because this is actually a bit of a slower pace than the MIT classes I was doing before. If it looks like, okay, I'm not going to be going right to the wire, I'm going to be going a little bit early, like I might be able to get done in 3 weeks instead of 4 or whatever. If it looks like it's like that, then I'm probably just going to invest more time in going deeper into really understanding that. So I might do extra Feynman techniques. I might play with the formulas more. I might tackle more problem sets. I might really challenge myself, because my goal here is to try to get some level of depth in a month's time. If it looks like it's way too easy. Now, as I mentioned, I did watch some of the classes before and I did glance at the problem sets, but haven't really done it. So if it looks like, okay, actually doing the MIT style, maybe I'm done in 2 weeks, I don't think this is going to happen. But if it does happen, there are more classes in this sequence. So I am going to be doing this for a month. So if I really felt like, you know what, I've got this, let's move on, then I would probably do, I think it's 805, which would be the next one. I think it's 805, the next quantum mechanics one. But I'm not too worried about that. My goal is to have an intuition. My feeling is that the difference between 804 and 805 is not so much the fundamental intuition about quantum mechanics, but it is the complexity of the problem. So I think those problems involve multiple particles in multiple dimensions. And so the math is harder, but the intuition is essentially kind of the same. So I think I'm going to focus on this class. So let's move over. So I'm going to switch between different views here. I'm not super familiar with live streaming, so if there's technical problems, if I screw something up, I apologize in advance. I'm just trying to do my best while I do this. So let's start. I'm going to shift over to this view, which has my notebook, and you can still see me here. So let me get my pen out. And let's try to work out what's going on in the class. What is the plan? So I'm going to be I'm not going to put it up on the window because I think it's going to be too hard to read what I'm saying. But in another window, I'm going to be opening the actual class on MIT OpenCourseWare. So if I go to ocw.mit.edu and then I look down, maybe I can post the link in the chat. Hold on a sec. Let's go 804. Right. Okay, here we go. So this is the one taught in spring of 2013 by Alan Adams, and I believe Barton Zwiebach also teaches a few classes, but it's mostly Alan Adams. And this is a really good class. I watched some of them already, just sort of in preparation for this, like about a year ago. And he's just a great lecturer. And this is one of the reasons I wanted to do an MIT class, is just because they're such great classes. I mean, not all of us can go to MIT, but they really do have excellent materials for learning. And I think if you are up for the challenge, they're really great. So let's look at the, let's start with the lecture videos. I have downloaded all of these previously, so I won't be streaming them, but this will get an idea of how much we have to learn. So we've got these lectures here. I'm going to be going in the actual lectures page. I think maybe I should actually, maybe I should, I'm wondering whether I should, yeah, I think, you know what, I'm going to open this in a new tab and try to set up a new scene where you can see me doing this. Hold on a second. All right, I want this one here. And let's go add my video. And I want to have my good microphone. All right, I think, okay, so let's try this. Okay, so this should be updated now, so you can see me when I'm watching the stream. I've noticed that the browser sharing kind of function, it is, it can be a little bit laggy. So I'm going to just try to do my best here, but obviously go to the link I posted in the chat if you want to look at it yourself. I just want to show you what I'm looking at while I'm looking at it. So here we've got the lecture videos, and this will give us a rough sense of how much content there is. So we have 1 all the way till 24. So there are 24 lectures, and they are, how long are they? Let me just stop it just so I can see how long it is. So it is an hour and 16 minutes. So I think these ones are, it's 24 lectures at an hour and 15 minutes. So let me just write that down here. So we've got 24 lectures. I'll just write here, this is going to be QM planning. So what I'm doing right now is just planning out how I'm going to study this. And just the first thing is like how much material there is. What would be a good way to schedule going through all the content? So we've got 24 lectures, and they're each an hour and 15 minutes-ish. I might do some of them on a faster speed, but the math part is kind of hard. So I think it might be kind of a mix of like when he's just chatting with the class, I'll go to a higher speed. And when he's doing the equations, it's probably going to be a normal speed. I'm not going to assume that this is going to be a lot higher, faster than 1x, just because I think I have the time to do it at a normal pace. And I think there's enough math that's happening in the class that if I go faster, I'm not going to be able to follow it. So it's 24 lectures at an hour and 15 minutes-ish. So if we kind of add that up, well, we've got 24 hours plus an additional divided by 4. It's another 6 hours. So we've got about 30 hours here of lectures to watch. Now, as I mentioned, my project is going to be 8 a.m. to 11 a.m. and then 2 p.m. till 5 p.m. I'm thinking I'm going to stick with this. There's obviously the chance that this is not enough time and that I'm going to require more time than this, in which case I might stretch out the schedule a little later. I don't think I'm going to do that. I think this should be fine, but if I really need to, I might stretch it out. But in this case, this is about 30 hours a week. Let's look at the calendar for April just so I can see how many extra days I have of this, because it's 6 hours a day. All right. So we have 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So we have 22 days at 6 hours each. All right, so that's 20 times 6, that's 120, plus that would be 132, I believe. You guys are going to see me screw up basic math pretty soon, so just enjoy that. So 132 hours. So, I mean, it's roughly a fourth. if I spend my time watching them 1x, I need about 1/4 time for lectures. I think the rest is probably going to be mostly on problem sets. Now, the basic material I have, so let's go back to this view right here. The basic material I have, hold on a sec. Where is my, where's my screen here? Oh, here we go. So the basic material I have is, I have the stuff from this class. So let's look at the assignments. So we have 10 problem sets with solutions. Now the problem sets at MIT are more elaborate than the ones on an exam because the assumption is that the students are working on them for a long period of time. So sometimes you will have problems that they're not harder materially, but they maybe involve more work. So you have to, like, it maybe takes you half an hour to solve a problem rather than something which has been simplified enough so that if you know the subject, you can solve it in an exam condition. So these 10 problem sets, I'm not quite sure exactly how long they're going to take me. I think that I'm probably going to do them mixed in with the class. So during the MIT challenge, my strategy was usually to do all the lectures first and then do the classes. Now, this has an advantage in terms of being really good for scheduling the time because then you don't get bogged down. One reason I would do this is that if I'm doing a class, let's say in 10 days, so I've got 2 weeks of real time to do it. Doing all of the lectures in, let's say, 2 or 3 days it's like it blows past you. So you probably haven't learned everything, but you've got a good enough coverage that you can start doing the problem sets, and then you know where things are going to be difficult. So you don't, let's say, spend a whole leisurely 3 days on the stuff that, oh, I get this stuff is easy. And then you get to the hard part and you don't have enough time. So one reason for doing it that way was for scheduling. But the other thing I don't like about that is that it means that your lecture watching is a little less efficient because you're going through the class completely first. So by the time you do the problem sets, you might have a case where, let's say there's a concept in lecture 20, which you're kind of like, oh yeah, I get that. But you don't because you had to understand a problem that was done in lecture 10 and how it was actually worked through mathematically to go forward. Because I think the math is going to be quite difficult here, as opposed to just understanding things at a very high conceptual level, I do want to mix them in. However, I'm also not wanting to get too into doing the problem sets and then skipping ahead to doing lectures, so that, let's say, I'm doing the last lecture on, April 28th, because my hope is that I should have covered the entire class so that I can actually identify, okay, what needs to be worked on, what skills need to be worked on. So I think what I'm probably going to be doing is about trying to finish all of the lectures. Let's try to finish all the lectures by about halfway. So I think April 15th. Let me look at how many days that actually is, because we've got weekends and stuff. So the 15th, if I can finish that, that would mean that I have to do it in about 2 weeks. 2 weeks-ish would be finishing all the lectures. And so during this time, I might not finish all the problem sets. So the goal here is not to do the entire class and make sure that I'm up to date with all of the problem sets. Rather, it is, let's make sure that we've covered the entire class so that I can get a sense of what's difficult, what's easy, and I can focus my resources. Now, I would like to try to do all the problem sets at minimum. I think doing problem sets is obviously the way you learn a subject like this, so the more problem sets I do, the better. At the very least, I would like to work through these problem sets from the actual class. We'll see whether I have enough time to do every single one of them. On the other hand, I'm hoping that I might have more time, so I might be able to do more problem sets. So this is not the only class that they have. There is also other versions of 804. So if I think I might be able to go back and look at other classes. So for instance, this is spring of 2016 and is taught by Barton Zwiebach, who also does those. And I believe there are also assignments here as well. So we have problem sets. I don't know whether these have solutions. They may not. Same with exams. Yeah, I think these don't have solutions, but they have material. Now, in addition to these classes that are on OpenCourseWare, there's also another way you can get classes which is not as well advertised, and that is by using MIT's course platform for their own students. So OpenCourseWare is meant to be for like everyone to access, whereas Stellar, which is what MIT students use to log in to access their classes, also has material. So if I'm missing material, I get it from Stellar. And Stellar is an example of like, there's no final exam with solutions in this class. So I could do a final exam. They do have a final exam here, but oh, this is the old class. Let me go to the class that we're actually going to be doing. Where is it? Okay, here we go. So this class, if I go to the exams, you see exam 1, exam 2, final exam. These do not have solutions. So the MIT challenge, a big part of it was that I'm self-grading the exams. I mean, I could try to hire someone to grade this, but that's difficult and time consuming and not really what I want to be doing. So my goal is to do this on my own, like try to do what you would be doing if you were doing this class. You're probably not going to be hunting down an MIT professor to hire them to grade your exams. So what I'm going to be doing here is using a final exam that is not from here, but is actually from Stellar. So Stellar, let's just load it up right now. Let me just Google it. Stellar MIT. So Stellar is what MIT students use to access their online materials. This is not meant for me. This is meant for MIT students. And I think, actually, I think I have to go, let me do Stellar MIT 8. Okay, physics course says. So you see here, it says access and it says class, MIT. So class means that when I try to, let's say I try to go to this quantum physics class, and it's going to say, oh no, you need to log in because you're not an MIT student, which I'm not. So, okay, all right, well, that's too bad. Yeah, see, we've got some stuff here. Oh, this is how I know which textbook I'm using. It's from here. But if I try to, so I think this Piazza, this is a new system. They didn't have it in the MIT challenge. This Piazza, I think, is where you access the class material. So if I were to click on this, oh, you forgot to log in. Okay, so I'm not an MIT student, so I can't access this. I can't access the ones that are class. I also can't access the ones that say MIT. During the MIT challenge, I did have a few insiders at MIT that when I was really missing exams, they could download them from this one because they had MIT login credentials, but I don't have that either. So what I have to look for is public. So when you see public here, this means that it's like OpenCourseWare. You can access this material as well. So I just kept going through this until I found one for 804 right here. And this one, fortunately enough, if I go to, where's the materials, you can see that there's more materials here, so I can access more materials. And there was past exam, I think. I was able to find an exam solution. I might be able to not find the exact one that I found before. No, this is not the one that I found. In any case, I did find solutions for the exam that were done for that class for someone else. Maybe it was a different one. Maybe they have another one here. Yeah, so some of these older ones have, I don't know, this might be it. It might be from fall 2010. But let me go exams here. I think, no, it doesn't seem to be. Oh, okay, here we go. Practice final exam. And then I think there are practice final solutions. So this is if I want to do an exam like, MIT classes, this is how I'm going to have to do it. I have to do it from the Stellar platform. So there are more materials though. So I just want to give that impression that it's not just the case that I have only this class to go on. I have all of the materials. I also have my book, which is from that class that I can't access, the Introduction to Quantum Physics. And I haven't read through it yet. I thought that would be kind of cheating a little bit to go through the class a little bit early and read through the book. So I don't know what they have in terms of problem sets here, but there's also stuff I can work through in here. So in terms of material, try not to think of this like an actual class where you have a set amount of material to go through, because the reality is, if I look at it, what we actually have here is we have, this is the 804, 2013 material. This is, let's say, we'll just branch it out. This is other MIT classes, but then there's also, other resources. So there's the textbook, there's going to be other websites, there's going to be, other problem sets from other places. So if we're really looking at it from the goal of that I stated at the start, which is I want to get an intuition for quantum mechanics and quantum physics, then what that's going to mean is that I have a lot of resources to choose from. For doing the final exam, this is going to be the stuff that matters most, and we do have quite a bit of resources there. So I am going to focus on these first because they're going to be, you know, I'm going to make sure that I don't get blindsided doing the final exam, that it has concepts that like we didn't cover that, so I have no idea how to solve those problems. But on the other hand, there's going to be a lot of basic concepts that are similar to every quantum physics class that I can go to these other resources for. So I'm going to start with that. In terms of the planning then, okay, so let's go back to our original sort of, or my original plan here of doing them by the 15th. So if I'm doing them by the 15th, we've got 24 lectures. So that is actually how many days? So if I look at it, I've got, well, we got today. So we've got 10, let's say 11 days. So if you have 11 days and we have to get through 24 lectures, then that means we need to have slightly over 2 classes per day. Now, if I'm doing 1 hour 15 for this on the live stream and I've got 6 hours a day, you know, I'm probably looking at each morning I do 1 or 2 classes. I think what I probably want to do is 3 classes to begin, and then I might slow it down. So I might even in this 15-day period start with a little more classes and then shift to do more problem sets later. So this is going to be the rough schedule until the 15th. Once it's the 15th, it's going to be all practice. So practice, Feynman techniques, going back over the material. So that's going to be all just revising, studying, really mastering the material. Whereas in this period, I may skip over some problem sets. I may not do all the problems. I may just focus on a few of them just so that I can keep pace and focus on the stuff that I find most difficult and that kind of thing. I'm also going to try to, in this period of time, identify what are my gaps. So that it may also be the case that I'm not doing problem sets for this class, but I'm going back and I'm revising linear algebra, revising other concepts from previous classes so that I can kind of get up to speed so that when I'm watching the lectures and they're doing, you know, some kind of calculus or algebraic manipulation, okay, I kind of have an understanding what they're going for. So let's go through some of the problem sets now, because I think this is probably the right step to take, is to look at what are going to be in the problem sets. I'm not going to understand them right now or understand most of them because, as I said, I did listen to some of the lectures, but I haven't done any practice. And the lectures I did listen to were almost a year ago, and these are all kind of hard math problems. So let's go through some of them right now. So let me just switch back. Okay, let's go through some of these assignments now. I have downloaded all of these, but let's just open them up. So this is problem set 1. So I'm just going to read through these problem sets, just skim them briefly. I'm going to try to go through all the problem sets just so that I can get a feeling of like what's difficult. I guess before I move on, does anyone have any like thoughts or questions about what I'm doing right now? Because I haven't really dove into the learning process yet. All right, so we have some. Okay, that just looks like some normal comments. All right, I guess we can move forward. So this is the first problem set. This is just gonna be going through my head as we do it. So this has some readings. I don't have any of these textbooks. So these are all textbooks. So I'm done for the reading. I can't do the readings, can't follow it along. So I'm going to have to just know what they're talking about and try to match to this book if I want to have some kind of additional explanation. So let's read question 1, radiative collapse of a classical atom. Suppose the world was actually governed by classical mechanics. In such a classical universe, we might try to build a hydrogen atom by placing an electron in a circular orbit around a photon. However, we know from 803, the class that I didn't take, that a non-relativistic accelerating electric charge radiates energy at a rate given by the Larmor formula. This d over dt equals -2/3 q squared a squared over c squared in CGS units, where q is the electric charge and a is the magnitude of the acceleration. So the classical atom has a stability problem. How big is that effect? So you know what? I'm going to try to switch this to, I'm going to add my note camera so you can see me taking notes while I'm doing this. 1 second. Let's bump it up here. Let's go here. 1 sec. All right. I have no idea whether this is going to be visible. It's probably, even if it's not visible in the live stream, it might be visible in the recording, which is part of what I want as well. So let's flip the page over and start with problem set overview. So this is going to be like kind of a pre-test, almost pre-test, or more like pre-review, because I'm not actually doing these problems. I'm just going to look at them and kind of like try to think through some of the basics of like how I would solve that, so that I can kind of get a sense of where I sit. So in this case here, the radiative collapse of a classical atom, I think the idea is that if we know from 802, which I did take, of electromagnetism, we know from Maxwell's equations that when you move a body that has an electric charge, so in this case an electron has an electron, when you move a body, it generates a magnetic field. This is how, you know, dynamos work and this kind of thing, is that when you move a magnet, it generates a magnetic field. And then at the same time, a changing magnetic field generates an electric field. So this means that when you accelerate, you create a changing magnetic field. And when you create a changing magnetic field, you also create a changing electric field. This changing magnetic field, changing electric field is self-propagating. So what happens is you change the magnetic field, you change the electric field, and the result is light. And so what this is saying essentially is that because it's on a circular orbit, it's constantly accelerating, just like how Earth revolving around the sun is constantly accelerating towards the sun, and it's only its own momentum that keeps it from falling in. And because it's accelerating at all times, it means that it must be radiating these photons, because there's a constant changing electric and magnetic field. And because it's radiating photons, because it's radiating this electromagnetic wave in a classical simulation, it's losing energy. And because it's losing energy, it's losing speed. And because it's losing speed, it's giving off this kinetic energy. It means it's going to be spiraling into the center of the atom. So if we've got this this kind of orbital model of the electron, this means that on a classical account, it doesn't stay like this. It must go like this. And this equation I'm looking at here is basically how fast does this happen? So it says show that the energy loss per revolution is small compared to the electron's kinetic energy. Hence, it is an excellent approximation to regard the orbit as circular at any instant. Okay, so this is going to be important for the, I guess, for the calculus, the fact that it's mostly a circle. So even though this spiral is not actually circular. Using the typical size of an atom, 1 atomic radius, and a nucleus, 1 femtometer, calculate how long it would take for the electron to spiral into the proton. So we want to see how fast this happens. So I need this equation for this. Compare the velocity of the electron, assuming an orbital radius of 0.5. Is that angstroms, or I think that's actually angstroms, not atomic radius. I will find out. That's something I don't know. So I'm just going to put that right here. So we'll see what this actually means. To the speed of light, will relativistic corrections materially alter your conclusions? So does the fact that the electron is moving very close to the speed of light and that there's time dilation, so does that materially alter your conclusions? I don't know. We'll find out. And then as the electron approaches the proton, what happens to its energy? Is there a minimum value of energy the electron can have? So I think this is asking, like, does this stop at some point? Like, does this like form a stable orbit somewhere? You know, whether it's elliptical or circular or something. I want to say no. I don't think there is. I think it probably just goes straight to the center. All right, let's go to the second question here. I'm just going to, this is PSET 1. I'll just put that here just for reference here. So number 2, dimensional analysis. So dimensional analysis is knowing the fact that when you do physics equations, for instance, it's like 5 meters divided by 10 seconds equal 0.5 meters per second. This is the dimension right here. The meters, the seconds, the meters per second. And so if you're doing a complicated physics formula, one way to tell whether you did the formula right is if you keep these dimensions and then you end up with the right units. So the units are meters per second, or the right units you're looking for, like, something complicated. If it's the right dimensional analysis, then that's usually a good indicator of, that at least you didn't do anything too stupid with calculating the problem. Gravitational bound states. Consider a particle sitting on a table which is kept from floating away only by the force of gravity. Okay, so like pencil on this table. This system is characterized by just 3 physical parameters: the mass of the particle, mass of my pen, the acceleration of gravity on Earth, 9.8 meters per second squared, and Planck's constant. Why is it formulated by Planck's constant? I don't know. Okay, Planck's constant, call it h bar. I don't know what's the right way to say that. H bar equals 1 over 2 pi h. The energy given by E equals 1/2 mv squared plus mgx. So this is this formula, E equals 1/2 mv squared plus mgx. So this is kinetic energy. And this is potential energy. It's energy. There we go. If I'm not mistaken, and I believe the x is the height. Okay. So using only dimensional analysis, find the product of powers of m, g, and h bar, which give a characteristic energy E. So I don't know what characteristic energy means. For instance, right, E is proportional to m to the power of alpha, g to the power of beta, h to the power of, I don't know which Greek letter that is, whichever one it is, and solve for alpha, beta, and whatever one that one is. Can you find such a characteristic energy without using the Planck constant? Okay. So I have no idea what this means by this, what characteristic energy is, and what the Planck constant has to do with it. Repeat to find the characteristic length, time, and speeds for this system. So I need to figure out what this, so one of the questions right now is, what does characteristic blank mean? So what does this mean? I don't know what this means. All right, classically, putting the system in its lowest energy configuration, E equals 0, would require the particle to sit perfectly still, V equals 0, precisely on the surface, X equals 0. Using the uncertainty relation, delta X, delta P is greater than or equal to H bar over 2, to argue, briefly, that the particle cannot have E equals 0 while respecting the uncertainty principle. Okay, so I'm not quite sure what it means by saying classically and then talking about the uncertainty principle, but I think what they're getting at for this problem for part number 3, or part number A3, is that this, because we don't have, because of the nature of particles being like waves, I mean, this isn't a wave, this pen right here, right now, but because of their being like waves, it's not possible to know that their position and their momentum with precision. And so because of that, it must either be moving a little bit, like it must be doing this a little bit, or there must be a kind of ambiguity about where it is. So it must be kind of spread out in physical space, like a wave that's very very shallow and is kind of spread out. And so because of that, that necessarily means that this thing has to have a certain amount of energy. It can't just be 0, because that would violate that principle. So I need to show that mathematically. Part IV, number 4.
Use your dimensional analysis results to give a simple estimate for the ground state energy of this system. So I don't really understand how dimensional analysis is supposed to, unless I'm understanding dimensional analysis wrong. So maybe that'll be another thing. So I'm going to also put dimensional analysis, because my understanding of dimensional analysis was that it was going to be some kind of like, quick check that the dimensions are right. But this is sort of talking about a value, which makes me think that maybe I've gotten that wrong. So use your dimensional results to give a simple estimate for the ground state energy of this system. How does your estimate behave as H goes to 0? Does this make sense? Why or why not? Okay. All right, so I think this H is related to this Planck's constant, and as it goes to 0, something is going to happen in the ground state, and does this make sense? So I first have to understand the question, but maybe it makes sense, maybe it doesn't. All right, part 5, evaluate E, L, T, and V numerically for a neutron. So the mass of the neutron is 1.7 times 10 to the negative 27th kilograms. How high above the surface will the particle typically be found? Oh, okay. So I'm assuming that what this means is that we have to kind of figure out what a ground state. Oh, this system has been studied experimentally in neutrons. Oh, interesting. Okay, there's an actual scientific or empirically found answer for this. So how high above the surface will it find? So I guess we're imagining here that it's doing this as opposed to this kind of vibration. So it's doing this kind of vibration. And so I think we're supposed to try to find, given that it's vibrating, that we can find the expected value of this. I'm not entirely sure how I'm supposed to figure out, because there's two unknowns here. We don't know exactly how fast it's moving or how it's spread out. So I'm going to write down that as another note that I don't understand about this exactly. Is that, let me see if you guys can still see my thing. Yeah, I think you can see it. Is that how do we get, so this E of, what's the height? The height was X, I think. I think X was the height. So this is the expected value of X, I think. How do we get this when there are two unknowns? I think it's V and maybe X is this. Maybe I don't need V, but still, there's like they're both multiplied, so presumably they can both vary. Okay, I'm not sure. All right, now this is 2A. Let's look at 2B here. The Planck scale. The scale at which gravity, characterized by the Newton constant Gn, quantum mechanics h bar, and relativity c are all important, is called the Planck scale. Okay. Part 1, using dimensional analysis, our good friend dimensional analysis, which we have yet to fully understand. Find the combination of powers of Gn, h bar, and c, which make a length, we will call this the Planck length, LP. So again, this dimensional analysis seems to be figuring out when these things are going to be relevant. Powers of this is going to make the length. Okay. I think that we have to know the dimensions of these constants, because these constants have their own dimensions, I think. So I don't remember what they are. So I think that that's how we're going to get this, maybe. All right. Evaluate LP numerically and compare it to a typical scale for nuclear or particle physics, namely 1F equals 10 to the minus 15 meters. So I don't know what this F means. Okay. Repeat to find the Planck mass, MP, evaluate it numerically, and compare it to the mass of a typical nuclear constituent, like the proton mass. Do we need to understand quantum gravity to study nuclear physics? So given that we don't have a theory of quantum gravity and quantum physics works really well, I'm pretty confident the answer is going to be no. The gravity is not that relevant to these constituents, but I'm assuming that this calculation is going to show that quantitatively. All right. Number 3, de Broglie, I think I'm saying that right, de Broglie relations and the scale of quantum effects. A, light waves as particles. The photoelectric effect. So the photoelectric effect, I'll just go back here. The photoelectric effect was found out in Einstein, and I believe it was that if you shine light of a sufficient frequency at, I don't remember the exact experiment, but if you shine this light at an electric sheet, I think it will bump off electrons, so it will generate an electric current in the system. And this was the fact that the light needed to be of a certain frequency was evidence that that the light needs to be in certain packets as photons rather than just sort of a continuous wave, the way you might imagine, let's say, a wave of water is also made out of particles, but the way that, like, you kind of at a large macroscopic scale, a wave is kind of just a smooth curve. It doesn't have discrete wave packets. So this is saying, suggests that the light of frequency V, I guess that's maybe not V, maybe that's a different number. Here, I'm just going to put down these blinds just because they're getting some reflection. Okay. Oh boy. You're going to be seeing some lines on my face here while I'm doing this, it looks like. So, consisting of photons of energy E equals HV, where H is equal to 6.63 times 10 to the negative 27 erg times seconds. Visible light has a wavelength of a range of 400 to 700 nanometers. What are the energy and frequency of a photon of visible light? Okay. I think I should be able to calculate this from 802 stuff, but I don't quite remember the formula. But there's a basic, oh yeah, this is just frequency times H. So this should be just a pretty simple calculation. All right. The microwave in my kitchen operates at roughly 2.5 gigahertz at a max power of 7.5 times 10 to the 9 erg per second. How many photons per second can it emit? What about a low power laser, 10 to the 4 erg per second at 633 nanometers, or a cell phone, 4 times 10 to the 6 erg per second at 850 megahertz? So these, I think, are all solvable with 802. I think if I worked them out, I could solve them. 3, how many such microwave photons does it take to warm a 200 milliliter glass of water by 10 degrees Celsius? Okay, so we're just, heat capacity of water. So we're just gonna convert this into temperature. I think, again, this should be solvable with 801, 802. At a given power of an electromagnetic wave, do you expect a classical wave description to work better for radio frequencies or for X-rays? I'm not quite sure about what that question is saying. A classical wave description, as opposed to particles, I'm guessing. Yeah, I don't understand this question exactly. So let me just flip this over here. All right. B, matter particles as waves. If a wavelength can be associated with every moving particle, then why are we not forcibly made aware of this property in our everyday experience? In answering, calculate the de Broglie wavelength equals h/p for each of the following particles. An automobile, So I guess this is just the idea of like the wavelengths are so small for these really big objects that we don't notice their waviness. They look very solid. I think that's what it's going to be saying. So I'm not going to go through all these examples, but I think that's what that's saying. Number 4, double slit interference of electrons. Oh, so this is one of my favorite experiments that was described to me, again, without having a good background in the math from these books. But the basic idea is that when you have 2 open slits, normally the waves will go out like, I'm just going to slide this over so I can just make sure that you guys are seeing my thing here. So if you have 2 slits like this, they're going out like this as waves. And if we keep going, you're gonna, if you can ignore my thing, you can see that there's gonna be like points where troughs line up and points where crests line up so that these 2 waves overlap. And you get something that looks kind of like this as an interference pattern. And this is typical of all waves, even water waves should do this, or sound waves should do this. So if these were 2 speakers, for instance, and they were all playing like a perfect tone, so they're the exact same frequency, there should be parts in the room that you stand to and they'll get a little louder, a little quieter, like that. And this is the wave model. And the kind of surprising thing from quantum physics is that if you do the experiment, but you have some kind of detector, I don't really know how the detectors work, but there's some kind of detector, it stops doing that, I guess, and it just becomes what you'd expect if these were like little like bullets or something. That's the double slit experiment, this kind of crazy result. I don't know whether this is this question that was asking about this duality of the wave particle, or whether this is just talking about the wave case. What is this question for? Okay. So electrons of momentum p fall normally on a pair of slits separated by distance d. What is the distance w between adjacent maxima of the interference fringe? So this is the, crests plus crest is equal to double crest. That's the maxima of the interference fringe pattern formed on a screen with distance d. Oh, so this is like, what is this interval? That's what this is asking. Note, you may assume the width of the slits is much less than the electron de Broglie wavelength. Okay, I don't really know what that means for this experiment. I seem to remember doing something like this in 802, but again, it was like a decade ago, so I'm going to have to go back and relearn it if I want to work through these problems. B, in an experiment performed by Johnson in 1961, electrons were accelerated through a 50 kilovolt potential towards 2 slits separated by distance d. I'm assuming this is 2 times 10 to the negative 10 centimeters. And then detected on a screen d equals 35 centimeters beyond the screen. So potential, again, good way to think of voltage is it's like height. So when you think of something being accelerated to potential, think of it as like if electricity were gravity, if you were just like dropping an object off of a height. So for electricity, voltage is like the height. And so it's as if we kind of dropped this electron off of a building that was a certain height, and that height was 50 kilovolts. And so it falls, and it gains a speed as it falls. And so that we know what speed it has, so we know its momentum. And it's separated by this distance. And when it's separated by this distance, it's going between 2 to the negative 4 centimeters. So we've got like a very, very small slit space here that this is going through. And then the wall is, so this is like, what is this? Is 35 centimeters, and this distance here is 2 times 10 to the negative 4 centimeters. This is like, what is negative 4 centimeters? Is that, it's not a nanometer, is it? I'm not sure. Okay, a micrometer maybe. Okay. So, and the fringe spacing, calculate the electrons de Broglie wavelength, I think it's lambda, and the fringe spacing W. Okay. I think this is solvable with what I know right now from 802. What values would D, capital D, and W take if Johnson's apparatus was simply scaled up for use with visible light rather than electrons? Oh, okay. So here we're basically comparing this wavelength to the wavelength that we know from this question, visible light. And so we would just have to scale this down. So that should be pretty easy. Question 5. Electron diffraction. Watch this video on matter waves. Should we watch it right now? Does it work? Matter waves. Oh, this is a huge video. Okay, I'm not going to watch it right now then. Explain using diagrams and/or equations why there are diagonal lines in the diffraction patterns which appear at 1259. Okay, so this is a long video, so I'm going to have to make sure either if I'm watching it, I'll probably download it. Looks like I'm downloading it right now. Download it, I'm going to have to do something with that. Make sure I turn off my Dropbox syncing just in case it's affecting my latency here. Okay. In their classic experiment, Davison and Germer directed an electron beam into a nickel crystal at 90-degree incidence and placed a detector at an angle of theta from the beam. The electrons were accelerated by a voltage of 54 volts. They observed strong reflection. I think this is on these electrons into an angle theta equals 50 degrees. Using the de Broglie relation and the Bragg relation, compute the lattice spacing in the nickel crystal. How does this compare to the value of 0.215 nanometers measured by X-ray diffraction experiments? So I don't quite know what to make of this question. I think this is basically the same as the split experiment, but maybe is the idea that the electrons are like bouncing off these atoms? Is that what it is? Like it's like this, and that's forming the interference? I don't know. Okay, you know what? I'm gonna just leave this question for right now. Question 6: single slit diffraction and uncertainty. Visible light with a wavelength of lambda is incident from a distant source onto a single slit of width dx. It's incident from a distant source onto a single slit. Denote the propagation direction as z and the direction transverse to it with x. Assume that x is a few times larger than. Estimate the width w of the pattern observed on the screen that is a distance d much greater than lambda away. By assuming that the slit acts as a collection of emitters all oscillating in phase. Oh, okay. So this is now we're getting to questions that I don't really quite know how to answer. I think a lot of this is 803, this wave stuff. So we're gonna just might have to jump back a little bit and learn some of that if it's too hard. Due to this range propagation in the x direction. So I think the way this problem works is visible light with a light lambda is onto a distant source. So I think we have a single slit. And the light is going this way, so this is our z direction. I think this is our x direction, and this is wider in this case than the light wavelength. So in these examples, these slits were really slits, and in this one here, I think the idea of this one here is that we can kind of think of each of these points as kind of like an integrated emitter. So instead of like they're all releasing their kind of spherical waves, so it's going to be some kind of, I don't know, some wave like that maybe. I'm not sure exactly what it's going to look like, but in the photon picture of light beam after this slit comprises a large number of photons with a range of values of transverse momentum. Due to this range of propagation speeds in the x direction, different photons hit the screen at different spots. So some of the photons have a different amount of sideways momentum because they're spreading out this way. Using the knowledge of W, estimate the range of transverse values of momentum dpx, assuming dpx is much less than p, where p is the photon momentum. What is W again? W is, the width of the pattern observed. Okay. All right, so we're trying to get this thing here. And then since we know each of the photons went through the slit, we have effectively measured the x position of the photons at that point. The experimental uncertainty associated with this particular measurement is dx. So again, uncertainty principle here. Since the momentum of the photons in the transverse direction is conserved between the time they go through the slit and the time they hit the screen, we've effectively also measured the uncertainty in their transverse momentum values just after the slit to be dpx. Using the relation E equals this together with the expression for the photon momentum, E equals PC, show that dx dpx is approximately equal to h. This is a heuristic realization of the uncertainty relation which lies at the heart of quantum mechanics. All right, so I don't quite know how to answer this question right now. There's a possibility this is 803 and not 804, because 803 is waves. And this is all about waves, and it could be that I'm missing it. It could also be that I'm just not fully understanding the question, and I do actually have the tools to solve it, so I'm not going to rule that out either. But, I mean, we'll go through these problems, and if I need to go through the solutions or that kind of thing, we can do that. All right. Oh, and that is the end of problem set 1. So we have these 6 questions for problem set 1. So if I look through this problem set 1, it looks like some of the questions I have some way of solving it, and some questions I am not entirely sure how to solve. Now, because this is the first problem set, when is it actually released in the schedule? So let's look at the syllabus. Do they have a calendar? Actually, I need course calendar. Do we have course calendar? It doesn't have the course calendar here, or at least I can't find it. Oh, here we go. I'm silly, I couldn't find it. Okay, so problem set 1 is due like basically right after this. So this is probably mostly 803 if I don't understand something, or 801, 802, and I've just forgotten stuff from those classes. So if we look at these problem sets, yeah, they're coming in here pretty early. I think I'm only going to go maybe up to problem set 5 right now, which would be sort of before exam 1, because it's going to take a little too long and I'm going to get too far into I don't understand any of this for this to be a really good use of my time. But okay, so we've got these sort of things going on here. But basically by lecture 3, I know that if I don't know how to solve these problems and the solution is not like, well, it's some mechanism that I learned here, then the answer is probably 803. I don't know how relevant 803 is going to be going on to the exams or going on to later things. I think this is sort of a recap a little bit. So, all right, let's go back now and look at some of these other problem sets then, where we have assignments. So let's open problem set 2 now. Have I lost everyone yet? Well, we got 20 people talking here. Okay, so I unfortunately reading this and following the problem sets has been quite difficult following the chat. So I'll try to check in on the chat every once in a while, but I'm probably not going to be able to follow everything you guys are talking about at the same time. So let's go to problem set 2 and let's look at this one. So I think I'm going to get some more light here now. Unfortunately, I'm probably going to be going back and forth with lowering these blinds because I have a big window in front of me, which is nice for lighting, but it also changes throughout the day, so it might be getting too bright or too dark at some points. All right, problem set 2. So let's do P set 2 here. I think we're going to go up to P set 5 and just kind of like, I don't want to solve the problems. I just want to kind of get a sense of like, where do I stand with these problem sets? And I think the other reason I'm doing this, which I think is important when we're talking about these things of what we're doing, is I want to kind of figure out where I am at with understanding. So what things do I understand? What things don't I understand? And when I recognize that I don't understand something in the problem set, that's going to be very useful, because when it gets talked about in the class, I'm going to be like, oh, that's what they're talking about. Whereas when I take the class first, if I haven't done any of this, I'm not really cued to like, what do I need to be paying attention to, because I don't know what form the problems are going to take. So that's the reason I'm doing it this way. So let's go through the problem set number 2 now. So what do we have here? Wave riding mechanics is number 1. What is the difference between phase velocity and group velocity? Okay, so this one I definitely remember taking in a class. I want to say maybe it was differential equations, but I believe the idea is that, let's say we have a wave that looks like this. All right, so we have a wave. Now, there is some velocity of the individual peaks of this, and I believe this is the phase velocity. And then there's also some velocity of this whole packet at the same time. And they do not need to be the same. I believe that is phase versus group velocity. But again, I feel like I've covered that before, but I don't quite remember. Why do waves break on a beach? Waves seem to get taller as they approach a beach. Is this accurate or an optical illusion? Oh, that's interesting. I have no idea. Again, we're all talking about waves here, so this could be 803. Again, I have not taken 803. Maybe I should. Maybe I'm going to have to go through some 803 material. We'll find out. C, a surfer is waiting for a wave packet of ocean waves, which is approaching a beach. For concreteness, let it be an infinite linear beach with a beautiful beige sand, constant slope, warm air, little surf shacks, and ceviche bars every few kilometers. Love the humor here. To the surfer's frustration, the first few waves appear to dissolve before arriving. Is this accurate or an illusion? Use the difference between wave and group velocity. I mean phase. Phase and group velocity explain why big waves tend to approach the beach in sets. Oh, this is very interesting. So I have no idea what the answers to these problems are, but they are intuitive problems. So these are kind of things that I would like to be able to know intuitively. Number 2, why I don't play craps. Let S be the number of spots shown by a 12-sided die thrown at random. Oh, so this is basic probability stuff. All right, so calculate S. Oh, so S with this bracket notation. I want to say this is equal to the expected value of S. I think that's what this notation means. I'm not 100% sure. And then there's, I think that's what it is. I'll just put a question mark above it. This S, I want to say this is the standard deviation of S. Could be variance. Is it variance of S? Is it this squared? I don't know. Okay. Calculate. So, and then we want it for 2 die. So that's just, again, simple probability. 3 dimensions of, okay, all right. This is embarrassing, but I think this one means phi. This is one disadvantage of not watching the lectures first, is that you forget what all the Greek symbols look like, and so I look like an idiot when I'm doing this. So I will learn what the Greek symbols are, and I will say them correctly once we've done the lectures. But I think this is phi. Again, it's been about 8 years since I've done anything with any Greek letters. So what are the dimensions of phi of x? And this, so I think this means complex conjugate. Complex conjugate. And I believe complex conjugate is when you multiply it with this, it gets rid of the imaginary component. So when you do like this, oh, I'm not drawing this right. When you do this, it should only be real. I think that's the idea of the complex conjugate. So if we remember our complex numbers, so complex numbers have a real part and an imaginary part. So this is the real part. and this is the imaginary part. So basically, complex numbers are just two-dimensional numbers. I always thought the like imaginary real to be kind of like just a way of describing it just makes it sound more complicated than it is. So a complex number is like basically a two-dimensional number and like a vector. And so I think the conjugate is like if this is this number here, so it's up here in the imaginary and up here in the real. I think the complex conjugate goes here. I think this is the complex conjugate. So that when they get multiplied out, like if these are unit length, I think it would it give here? I think they would cancel. Okay, I'm not 100% sure what complex conjugate is, so we're going to have to also look this up. And we're also going to have to look up whether this means complex conjugate, but we'll find out later. So, okay, all right, number 4. This problem set seems a lot easier than the last problem set. Maybe there's more questions. And it does go up to 8. Okay. All right, 4, Fourier transforms. Okay, our good friend Fourier transform. So just to recap, Fourier transform. Well, this is a big subject, so I'm not going to be able to like give a full explanation of it, obviously. But essentially, you can think of two ways of making a function. So a function, you know, like I don't know, like y equals, let's say, x, and then the function is this, right? So one way you can think of this is that every single point, all the infinite points, are all made of like these little position components. So if you were to decompose this function, you could think of it as for every x, there is some y, some position. And this would be the kind of the normal way. I don't know, there's a different way of saying this. This is like the normal way of looking at a function. But for some functions, you can think of it a different way. So let's say we have y equals, y equals sine x. And then you have something that looks like this. I mean, excuse my my drawing right here. But you have this kind of function. Now you have something complicated. So every single y point has this kind of thing, right? But there's another way of doing it, which is you can actually represent any function. This was Fourier's brilliant insight. You can represent any function not as individual points, but as built up of waves. So built up of sine waves of different amplitudes, different phases, different frequencies, all built on top of each other. So even this wave is some complex assortment of these different waves. And so if we look at this wave here, it's very obvious what this wave is. It's a single sine wave of, you know, whatever frequency this is. So what the Fourier transform does is says, what if we took this function and said, what is the function of, instead of in the, you know, this is x, what if we took this as the frequency? And if we took this as the frequency, this function is pretty simple. It's just one sine wave of a particular frequency. Now, this function is going to be much more complicated in the Fourier transform. I don't actually know what it's going to look like. Yeah, I actually have no idea what it's going to look like. But essentially, this Fourier transform is turning it into a frequency domain, and that's useful for a lot of applications. So one example would be in audio processing. Frequencies are, you know, what you can hear. So what you are hearing is essentially the Fourier transform of sound waves, because it's all these pressure packets of high pressure, low pressure, high pressure, low pressure. But you're not hearing high pressure, low pressure. You're hearing frequencies of it. So you're telling that there's a little bit of a, you know, 200 hertz tone and a little bit of a 1000 hertz tone and whatever in your ear. So your ear is sensitive to frequency, so it's as sensitive to essentially the Fourier transform of the pressure waves that are hitting your ears. So this is a little complicated, but the idea being that when you're dealing with waves, when you're dealing with wave-like things, it's very often to look at them in the Fourier transform, because Fourier transform is in some ways the more natural way to look at wave-like phenomena, where they are made up of waves of different frequencies rather than made up of individual spikes of pressure or individual values happening at every single point. So that's the Fourier transform. So in 804 conventions, a function fx and its Fourier transform f little tilde of k are related by this. All right, so I'm going to have to remember this math at some point. So this is just the Fourier and inverse Fourier transform, I'm pretty sure. Okay. And then this x in the angle brackets, which if I go back is probably the expected value of x, is equal to the integral of dx p, but it's this big kind of, I don't know, fancy p. I don't know what this fancy p is. Pxx equals of this psi x. So this is some equation. I don't understand the equation. Using the definition of expectation values of powers of the momentum operator. Okay, all right. So now we're talking about something else. So let's just kind of just take a little. Did I write down 4 here? Yeah. So I'm just continuing 4. Okay. So what are some things that I don't know about this? So I don't know what momentum operator is. I'm not 100% sure on this bracket notation, but it should be fine. I don't know what big P is. So what is this P? Okay. All right. And also this theta function, I think I remember from chemistry that this is the wave function. I think this is the wave function, which would be like, like our particle, if it's actually a wave, looks kind of like this, let's say. And so, theta is equal to this. This is I think, but I'm not entirely sure. You know what I think it is? I think this P, because the wave function squared, I seem to remember this wave function squared is the probability of finding. Okay, so this is definitely expected value then. This bracket notation must be expected value, because if the probability of finding it is is this theta function squared, which is the magnitude? I'm not sure exactly what this is happening here, but I think this must be probability. So I'm going to say probability right now. I think this is probably probability. Probability of finding the particle at x. Okay. And so this must be the expected value, because if we take the probability times each value of x and we integrate it, that's going to be the expected value of x. No? Okay. Using the definition of expectation values powers. Oh, okay, so if we're talking about expectation, this is definitely expectation. So, okay. Expectation values of powers of the momentum operator. P hat n equals integral dx, this, okay. I don't know what this is, but okay, sure. The form of the momentum operator, P hat is equal to negative IH partial derivative of x. And the definition of the Fourier transform, show that this is equal to this and this is this. The relation PK, as discussed, that follows from the Born relation, this. All right, so we're definitely getting into material I haven't covered. I get the feeling, because we're now talking about some stuff here. I think this is now 804. So before, I'm not sure whether it was 803 or 804 material. This feels like 804 material, because we're now talking about particles. We now have these little phi, psi, whatever operators. So I think this is going to be from here. So there's a lot of stuff I don't understand, but so I'm not going to write all of it down. But I think we're now into 804. So I think once we go through the class, this should start to make more sense. I think just getting the rough picture of what I think they're getting at here is that obviously if we're talking about a wave, so the wave momentum is related to its frequency, right? So if we're thinking about like a photon, which is a wave, and has some momentum p, this is like related to its wavelength. And this is because we were talking about photoelectric effect, that, if basically photons that are higher energy are like striking something harder. Now, they're not going any faster, and they don't have any mass, but they do have a different momentum here. So this is photons. Now, with this being what the photons are, I think what they're trying to do in this problem is showing that when the Fourier transform, which is taking basically from something being complicated like this and turning it into, it's actually like just one frequency, it's just one point. I think what they're trying to say is that if this is the position where it's a fully spread out wave, then this is the frequency. And if this is the Fourier transform of this, then I think what they're trying to say is that you kind of, the momentum relation is related to the Fourier transform. All right, that's all I can really say right now. I think I got to go do the math a little bit more first and learn this class. All right, let's do question 5. Delta function. The Dirac delta function, dx, is defined by the condition dx is equal to 0, x equals 0, and infinity for x equals 0, or more precisely, the integral of this is equal to f0. 0 is a set of AB. So if I remember correctly, the delta function is a kind of, it's not even a real function. It's just sort of a fake function that has certain properties that are nice. And the properties are that it is infinitely thin and infinitely tall. So this is positive infinity, and this is like, 0 negative and 0 plus, bordering it. But that when you integrate the delta function, I think you get 1. So it integrates, it has like a mass of 1, even though it's infinitely thin and infinitely tall. All right. Evaluate the integrals from -1 to 3 delta this. Okay, so this is just a bunch of math right now. I think I could probably solve this right now, but I'm not going to get into it because I don't want to start solving problems yet. I'm going to run out of time. I want to review everything. So I think this is I can probably solve right now. And this is probably from different, I think this was from differential equations. They did delta functions, but it could also have been from my signals and systems classes they did in the MIT challenge, which had a lot of stuff with Dirac deltas. The two expressions d1x and d2x involving delta functions are equal for any smooth function f. Get another little integral here. Establish the following qualities. This is just going to be some math. So again, I think I should be able to do this if I haven't forgotten all of my calculus. But again, 5 should be solvable here. I think this is, again, should be solvable. All right, so 5, I don't think there's anything new to learn there, but I may need to brush up on old stuff. Question 6, qualitative structure of wave functions. Aside. In lecture this week, we looked at a number of examples. Example wave functions, sketch their Fourier transforms, and estimate our confidence and predictions for measurements of the position and momentum of the corresponding systems. In this problem, you will make those arguments precise by explicitly commuting everything we discussed. Okay, so this is from a class. I don't know which class this is going to be. Let's look at the calendar. Problem set 2 is due here, so it's probably, I don't know, L3 or L4 that we're going to be doing this. This is probably L3 or L4 that we're coming at. So consider a following non-normalized wave functions. What is the one? See problem 5. Okay, well, that's all right. For a particle in one dimension with x as a dimensionless variable. So this is just various particles. And then sketch the wave function. So this is a really good problem because this is basically like, okay, this is a bunch of math and you can solve problems with the math, but can you have a visual intuition for what's happening? So I like problems like this. Compute the Fourier transform. Sketch this, whatever this is. So I think I'm going to put this here as something I don't quite understand. Is my my notepad here? Oh, I think I'm going off the notepad. All right, let's go back. All right. Where will the particle most likely be found? What's the most likely momentum? How confident of these predictions are you? All right. Determine the normalization constant n up to an overall phase. So phase, if we remember correctly, is the difference between a cosine and a sine wave is phase. So this is the sine wave, obviously, and this is a cosine wave. They're exactly the same. The only difference is that the peaks happen at different times, and this is the phase. Calculate the expectation values of x and p and the uncertainties. So this delta notation, we were like asked, I was figuring out what the heck is this delta notation? Well, we'll see right here, it says uncertainties. Now, I still don't know whether quantitatively that means variance or standard deviation, but we know we're on the right track then. Okay. If so, how efficiently? Comment on what this says about wave functions of this form. Okay, sure. What happens to the shape of the wave function as a goes to 0? What happens to this psi tilde k? What happens to both in the limit a goes to infinity? What is a? Do we have a somewhere here? I don't know where a got introduced. Well, there's a up here, so a must be something else, maybe. Oh, okay. This is the shape of the wave function. So I think. All right. Oh, okay. So this is some other kind of function where a is determining. I think this is determining the width of the function. So what happens when it gets really, really narrow? What happens when it gets really, really wide? Okay. All right, let's do number 7. Number 7. Oh, I skipped over it. Why the wave function should be continuous. Consider the wave function, whatever this is, from problem 6, which is just a step function centered at the origin. Okay, I didn't even have to read it. They just said it. So we got this here. This is a step function. On first glance, this looks like a perfectly reasonable wave function. It's normalizable. So normalizable. That's another word here. So I don't know whether this is true of this, but when we talk about normalizing a vector, what we mean is we want it to have unit length. So we want, if you have like some vector like this, and we want this to be normalized, it would only be one length long. And so I think what this means when we normalize this is that this shaded thing is all the integral of this, like the area, is equal to 1. And I think that that's important because this wave function is used to determine probabilities, and the probability of, excuse my notation here. The probability of all the like events that could happen it's got to be equal to 1. Yeah, my notation is garbage, so just ignore that. I'm just trying to use it for illustrating. But basically, this should be normalizable because if you have some weird function, like this, for instance, is not going to be normalizable because it keeps going to infinity. And because it keeps going to infinity, how are you going to get this? You can't divide it by something to get the integral to equal to 1. So this is not going to be a good wave function. Delta x is finite, so meaning that it's not infinitely spread out in space. And its Fourier transform is simple. Okay. However, since it has discontinuities, so this is a discontinuity at these points, acting on it with the momentum operator leads to divergences. I think this is because in order to represent it, you need to have infinite momentums to make these corners sharp. That doesn't seem very physical. Let's make this precise. Determine the normalization constant and then calculate the uncertainty dx. Okay, so I think this normalization constant, again, is like, how do I divide this so that this area is equal to 1? And then the uncertainty relation is, again, how spread out is this? So this is some formal, like a number that indicates how spread out this is. Obviously, this is spread out, but I don't think it's going to be just that width. It's going to be some kind of number that's going to be related to that. Calculate the momentum, and I think this is like the momentum squared, maybe. By using the Fourier transform, you calculated problem 6. Note that your result for momentum 2 is divergent. Okay. Divergent. Okay. What must be true of the large K behavior of this K to ensure that this is finite? Continuous waves. We should demand that physical wave functions must be continuous. That makes sense. That makes sense. Okay. So it just basically means you can't have any gaps. So like, I know this looks like it's a solid line, but obviously in the actual function, you kind of have this, right? This is the actual step function. Like there's no line here, right? And because of this, there's this gap. And I guess what they're saying here is we're trying to mathematically prove that you can't have wave functions that look like this. Optional. Ooh, optional question. So this one's for fun. All right, as you have shown, the discontinuous wave functions in theta 7, which was up here. Oh, this is the step function, I think. Oh, gives divergent values for this momentum squared, and so seems quite unphysical. You have also shown that its Fourier transform falls off very slowly for large K. This problem will explore the connection between continuity, finiteness of this value, and the large K behavior of this psi function. So K, I think, I'm going back here, but I think that this K, so we have this, and we have, I think this thing is the Fourier transform of this. Because I seem to remember K is usually the variable they use for the Fourier transform. And I do seem to remember earlier when we were discussing these problems, this tilde was like meant Fourier transform. So when we're talking about this psi, we're talking about now the wave function in this momentum space, in this frequency space, as opposed to the actual position. All right. Consider the smooth function, whatever this is. Oh my God, hyperbolic tan. This looks like it's going to be fun. Sketch this for various values of b to convince yourself that this will well approximates this as b goes to 0. Argue that for b, blah, 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 n is roughly independent of b. All right, so this is a bunch of math on this. I don't think I'm going to go through all of this. Okay, so we have now finished going over problem set 2. Now, what will I say about problem set 2? Well, first of all, it looks like it's a lot more based on 804. I don't see as much stuff that is, again, I'm basing this off of the fact that I did watch some of the lectures about a year ago, so I have like kind of that abstract sense of, okay, I kind of remember them talking about this a little bit. So if it looks like I'm just like, how am I getting it from this? It's because I did watch some of the lectures, as I said, about a year ago. So this feels more like what they were talking about. Problem set 1, not as much. And it may be the case that problem set 1 depends on a lot more on the waves class. So in some sense, it might be that problem set 1 is actually going to be harder, because it's going to be based on more material I haven't actually studied. So, all right, let's go on to problem set 3. Let's go assignments. Problem set 3. I'm just going to check in the live, see how you guys are doing. Oh, look at you guys chatting away. I'm sorry I'm not able to really follow you with with this chat. I was hoping I was going to be able to be a little bit more engaged, but it looks like there's a lot of discussion that I am not able to completely follow with also reading the problem sets. Oh, how do I get this page back? Okay, there we go. So let's go through problem set 3. I think I'm probably going to be able to get through the first 5 problem sets here. I'm not going to do any of the lectures. I'm going to start doing the lectures in the afternoon, I think. Because I think going through these problem sets is good. It gives a kind of grounding of where I'm at, what I need to be paying attention to in the lectures. And I think getting up to the first 5 problem sets is probably about as far out as I want to go, because I think that's the first 10 lectures. Yeah. So problem set 5 is due at lecture 10. So I'll know that when I hit the lecture 10 mark, I should probably do the last 5 problem sets as a gap before going through the next 14 lectures. So they are a little bit more dense in the beginning as well, which might be a factor for learning things as well. I think it's important to not get too bogged down on the early problem sets, just because they may not end up representing a full, they might be too focused on the beginning material. And if that material is easier, which it often is in a class, I'm going to give it too much weight. All right, so problem 3, question 1. Mathematical preliminaries, linear operators. An operator, O hat, is said to be linear for any functions fx and gx, and for any constants a, b, such that the operator a fx plus b gx is equal to a of a, okay. So, and this is something I do remember from watching the lectures about a year ago, and I thought this was kind of cool because this has a natural analogy to programming. But what an operator is, so we can think about a function, and a function takes values. So you can do like f of 3, f of like the sine of pi. You can take like f of I don't know, the constant e. This is what a function is. It takes values as input, and then it gives you an output, which is also a value. Now you can do functions that take different values. You could have a function that takes 2 variables, or you could take a function that, let's say, takes, you know, a vector, or, you know, maybe even a matrix, right? I don't know whether there's a special notation for matrices. I'll just put a capital M. So you can do functions, and this is very similar in programming, where you have some sort of function, let's say like, you know, calculate x, and then you have some function and you put in like y, and then, you know, it return y. Whereas operators, and this is again me kind of cheating from having watched this a little bit ahead of time, is operators take functions and return other functions. So in this case, it's, let's say our operator O is taking not values, but in this case, f. And it is returning another function g. So the way to think about it is that, so an f is a mapping of, let's say, like points to points. So f is going to be take, you know, y equals, or sorry, x equals 3, and then that goes to, you know, y equals 4, right? Like that would be f. Whereas O is taking a function that, let's say, looks like this and turning it into, you know, a function that looks like this, right? So it's not taking an individual point, it's taking a whole function. So what are some, and this is talking about linear functions. Now, I think this is going to be related to, again, like linear algebra and these kind of things. And basically, it looks like what it means is that if you take the operator of 2 functions added together, and they will be separable like this. So waves themselves, I think, are linear. I'm pretty sure that's true. So if you have this wave and you like add it to this wave, it's going to be just sort of a linear sum of every point on the thing. But if the waves, you know, move past each other the way waves do, it's like they don't interact. Like you have, let's say, this wave, and then they're getting closer, and then they overlap, and then they start going their own direction. So I think this linearity is an important factor, because if the waves did something complicated and it was dynamical and it is just changing, the math is going to be a lot harder. You're not going to be able to separate things out. These are different types of operators, and it's asking which ones are linear. So one is identity, one is squaring it, one is derivative or partial derivative. This is, I don't know what this means. dx, oh, I'm used to thinking of this x as being a meaning first derivative, but maybe it doesn't mean that. X prime, okay. Adds 3, maps to gx, translates by L. All right. What are the eigenfunctions and eigenvalues for the following operators? Okay, eigenfunctions. Let's see if I can remember this. So, eigen is a German word, and I think it means characteristic. So when we think about a matrix, this is like linear algebra. When we think about a matrix transforming something, a lot of what we're talking about when a matrix transforms something is that this matrix has basically a matrix it can take some input vector and give an output vector. So an example is maybe you have a matrix that takes everything and stretches it like this way, right? So this is what before and after. So what the eigenvectors are for this matrix, or to use the translation in English, what are the characteristic vectors, or what are the ones that are only changed by a factor of scale? So if you put in a certain vector, like let's say it's scaling this way, and then all it does is it gets longer or shorter, then this is an eigenvector of this system defined by this matrix transformation. Whereas this one here, this vector is, for instance, not an eigenvector because it's changing direction. Now, the amount that it changes is this eigenvalue. Now, one of the interesting things is that you can have, I think, complex eigenvalues or complex eigenvectors, so that, for instance, a matrix that, let's say, rotates everything, so it just rotates everything by 45 degrees, would have a complex, I believe, eigenvalue. Or maybe it's a complex eigenvector. Maybe it's a complex eigenvector, and then the value would be just how much it scales. So this maybe would be 1 in this case. Because obviously there's no vector you can put in a real term that is going to not, like they're all going to rotate, so they're not going to ever just scale. But there is going to be something that, if you can imagine, let's say it's like sticking up out of this page right here, like it's in this kind of complex domain, that it's not actually changing. So that's the eigenvector and eigenvalue. So what is an eigenfunction? Well, I believe that an eigenfunction would be a function that when you apply an operator to it, because a matrix is like just transforming vectors, an operator is transforming functions. So it's taking f to g, just as a matrix M is taking, let's say, a to b. So if an operator is transforming functions, the eigenfunction would be what would only change by a factor of scale. So we know for, let's say, taking a derivative, that the eigenfunction is the complex exponential, because we know that exponential functions, when you take the derivative, what happens when you take, dx of e to the x, you get e to the x, right? Like this is, and if you have like dx to e to the 2x, pretty sure you get 2e to the x. I'm gonna feel embarrassed if I'm screwing up my basic calculus here, but it has been 8 years, so you'll have to forgive me if I make some mistakes. Oh no, e to the 2x. So if you do this, then because it's only a factor of scale, otherwise the eigenvalue or characteristic value, because it's only a scale factor, this function or these families of functions are all eigenfunctions of the operator of taking a derivative. So that is what the eigenfunction and eigenvalue is. And I remember doing this in linear algebra, and I remember finding eigenvalues and eigenfunctions super confusing.
at the time. So this is an insight that took me a while to get to, which is probably just because the way it was explained to me, I just didn't understand it. But this is a standard way to explain it, is that for things that transform other things, the eigen ones are the ones that, it's the thing that doesn't change. It's the class of objects that don't change other than a scale factor under the transformation. So C, show that the eigenfunctions of whatever this is are of the form whatever this is, where B is a complex. All right, so I don't know, where's TL? Oh, translates by L. So we need to show that the eigenfunctions of this are things with this complex exponential, and it's a periodic function with period L. Okay. I think I could probably do that now, but let's move forward. 2, mathematical preliminaries, more on the translation operator. As we've seen, the position operator, x hat, acts on the functions of position, fx, as x hat fx is equal to x fx. So I have no idea why this is. I don't know what this is doing. And why would, so I'm going to put that as, I don't understand why it would be x times fx. So this is y. And so I don't know. I don't know this. Meanwhile, the derivative operator d hat acts on functions of position as d hat f of x is equal to partial derivative of x times x. Okay. Translate by L operator acts on the functions of the position of fx x minus L. So this position operator is multiplying it by the position. I don't really know what that does, but okay. Show that two operators are equal. Both operators act identically on an arbitrary function fx. If a hat is equal to b hat, if a fx is equal to b hat fx for any function fx. Show that TL commutes with the derivative operator. I need that TL. So we're just making some proofs about these operators. Commutes with the operator. So this is something I don't know. Okay. Show that this to define a Taylor expansion of EDX. I don't know what RHS is. You need to see show that this, so this notation of operator 1, operator 2 is equal to, I don't know what this notation means. So this is some new notation that I got to pay attention to. Use the definition of the position operator and the definition of the Fourier transform to determine how x hat acts on the Fourier transform. Okay. Verify that the commutation relation. So this is commutation, I guess. Whatever commutation means. I've now linked the two. Holds whether acting on this function fx or its Fourier transform f hat of x. What lesson do you take from this? Okay. All right. I mean, there's some stuff I don't understand there, but you can fill in those blanks later. The meaning of the commutator. Oh, look, it's just in time. We're finding out what the commutator means. Let A and hat be linear operators, and let C hat denote their commutator, i.e. C hat is identical with A hat B. Show that C hat is also a linear operator. So this is interesting because it's saying that, like, I can so the operators can not only take functions, which are functions of value. So let me just write that out. So it's function of x, let's say. So this is function, this is value, and this is operator.
But it looks like if it's doing something with these, then an operator can also take other operators. This is an op taking another op, which I guess if it's a kind of function, I guess that kind of makes sense. But I don't know. I'm just thinking from a programming perspective, like you could take a function that is defined to take functions that take other values, or you could take a function that's designed to take functions that take other functions. This seems to show that it doesn't matter, which, I'm not quite sure how that's going to work out mathematically, but I think that's an important observation to make. Suppose that A and B share a common eigenfunction. Okay, show that AB must be annihilated by the commutator. I see this equals 0. Suppose AB equals 0. Such operators are said to commute. So commute means that, I guess, can A and B share common eigenfunctions? So this is going to involve some math that I don't have yet. Suppose A and B commute. Are all eigenfunctions of A necessarily also eigenfunctions of B? If so, explain why. If not, give a simple counterexample. All right, let's move on. 4. Operators and commutators in quantum mechanics. As we have seen in quantum mechanics, position and momentum are represented by the linear operators acting on the wave function psi of x. With all this, representing observables as operators implies a host of facts about observables in quantum mechanics. In this problem, we will use the results you derived above about mathematical operators properties of observables in quantum mechanics. So observables, I'm going to make a guess, take a stab at the observables are the things that we can measure in experiments. That would seem to be what observables means, but maybe that's not what that means. Using your results from the previous 3 problems together with the representations of the momentum and position given above, show that the position momentum commutator takes the value p hat x hat, whatever this. All right, this is more information about this. Okay, so I'm going to kind of skim over this now. It looks like we're reaching kind of maybe the end of where I can understand these problem sets, but let's do one more, and then if it's just complete, like I can't understand any of it, then because we've done 3. I think this is a pretty good head start. So if I don't have to go to 5 if it's feeling too difficult. All right, PSEC 4. All right, we're also 10:14, so I'm going to try to go for another 45 minutes. I might go a little bit longer today, another 10 minutes or so, just to debrief a bit about what we're doing. I'm going a little slower now than I'm hoping in the later thing, because I'm trying to just get a hang of doing this live on camera, but work this out. Okay, problems at 4. Number 1, simultaneous eigenstates. So eigenstate, what would an eigenstate be? So now you can characteristic state. I don't know what a state is, but I'm assuming the eigenstate is some kind of state that is a characteristic state of the system. So let me just write down that guess. Eigenstate is equal to characteristic state of a system. All right. Your friend from last year's 804 argues the following. If a particle is in an eigenstate of a one-dimensional box of width L, then we know its energy exactly. We also know that the energy in the box is purely kinetic. Sure, okay, we know that. Hence, we know the particle's momentum exactly as well. This contradicts the Heisenberg uncertainty relation, since the uncertainty in the particle's position is finite, is less than L. Punch a hole in your friend's argument. Okay, so we need to know something about this. 2, formal properties of energy eigenstates. Given a physicist's proof of the following statements regarding energy eigenfunctions. A, we can always choose the right energy. We can always choose the energy eigenstates, theta E of x, we work with to be purely real functions, unlike the physical wave function, which is necessarily complex. Rather than if you find an energy is not real, it can always be written as a complex linear combination too. So I'm going to guess that this 2A means that energy it must be real. It must be a real value, you know? Like you never have a complex energy. That's what I think that means. And we have to demonstrate that. If Vx is an even function, remember even functions, guys? I'm going way back to high school math now. Is an even function, v negative x is equal to v of x, and the energy eigenfunctions ex can always be taken to be either even or odd. Oh, so we're trying to ask whether this thing is... Oh, that's kind of an interesting question. Okay, that's a good math. This is a good mathematical intuition question because it's asking you a general property, but like if you have the right intuition, this... I'm assuming this answer should be obvious. I mean, it's not really that obvious for me right now, but I haven't taken the class yet. C, the lowest energy eigenvalue, E0, corresponding to a normalizable eigenfunction is strictly greater than the minimum value, Vmin, of the potential Vx, i.e. Yeah, I have no idea. I have no idea what that means. 3, superposition in the infinite well. Verify on scratch paper. No need to turn this in. Well, I won't be turning any of them in. They're all on scratch paper. The results stated in the lecture for the eigenvalue of the energy operator for the infinite potential well with L. So this is a potential well. Now, again, this is me remembering a year ago doing some of these lectures. Potential well is that you can imagine a potential. So potential is just, if you think about gravity, for instance, gravitational potential is higher at a higher height. So the potential well is just an infinitely deep well, and then the particle has to kind of like live in this well, you know. And I think I remember it being an interesting problem because there's infinite potential on the sides, the particle, like essentially it can't exist here because it has to climb up infinitely high. And so at this point, it has to be 0. But because the waveform has to be continuous, you can't have this doesn't work, for instance, as a wave function because it's discontinuous here. It goes from high to 0. That you essentially you have to have it be like, I don't know whether you can see this. Can you see this? Oh, yeah, sorry. I got to get better about knowing where the camera is positioned so I'm not losing you guys here. So it has to be something like this, or this, or this. Basically, it just has to be such that these like potentials all hit 0 and it's all continuous. So there's only certain like frequencies. So one way of thinking about this is kind of like how a musical instrument, like if you blow in it, will have a certain sound, and those are the resonant sounds. And those resonant sounds are kind of like this, that they're the waves that match the length of the container. So when you like, I don't have a bottle here, but if you really blow on a bottle and there's a certain amount of air in it, it'll make a certain pitch sound. And that's because only sound waves of a frequency that matches that distance and that shape can easily be sustained. Everything else is kind of interfering and collapsing on each other. So this is similar to this, I think. So, all right, verify that this, and then we get some eigenvalues again, some math that I don't know how to do. Suppose that time equals 0, we place a particle in the infinite well in this really super complicated state. Each step knows you need to know in the functional form mentioned. So, okay, so I don't know. I'm not going to go through all this because there's a lot of math that I don't understand yet, but we've got basically just, a bunch of stuff involving that. Sloshing superposition. Consider a particle mass m. Play around with this applet for insight into the system. Okay, I'm also going to skip over this. Qualitative properties of energy eigenstates. Okay. All right. So I'm actually going to pause it right now on doing the more problem sets because I think I'm kind of reaching my my capacity right now for doing this. Now, I have about 40 minutes left, so I could probably go through some of the lecture, but this being the first day and all, I'm gonna just talk a little bit about what I did, why I did it, review some of the things that we sort of talked about. I'm gonna go a little slower than I maybe would do this if it were just me. Like I think if it were just me, I would just go right into the next lecture. But this is the first day, and I kind of want to explain my process as much as possible because then once I just start doing it, I can just keep doing it. And so why did I do what I did? So I think there's a couple reasons to do this kind of review of the problem sets first. So if we look at it, the first reason is that you want to kind of sense of what is it that you actually have to do. Now, I mentioned at the start that when I was doing this class, my goal was to get some kind of intuition. It wasn't necessarily to be, being able to do all these calculations perfectly, because in my real life, I don't really need to do these calculations. However, calculations are kind of the raw material for building an insight of why things are the way they are. So I don't think, and as I was saying this, I don't think if you avoid doing the math, you can easily get an intuition about what's actually going on here. But I think by doing the math, you can develop that intuition because you get a feel of the quantities and what things are going on with what. And then if you forget how to do the algebra and calculus, as you often do, what you're left with is the intuition, but the intuition was built up with the math. So I am taking the math very seriously here, and I'm going to try to be doing my best. I'm not going to be worrying too much about making minor algebraic and calculus mistakes. I mean, I want to try to do those as well as possible, but they're not my goal. My goal here is not to, as I said, to become a physicist. My goal here is to be able to have a good intuition about these things. And so if I do something, I'm like, oh, I made a simple mistake, I'm probably not going to be too hard on myself. However, if I'm doing mistakes because I don't understand how the problem works, or because I can't solve the problem, or because I don't have the right mental structures for the math, then that's different. So I'm going to be treating it like a real class, like I were trying to pass the exam, but my emphasis is going to be a little bit more on intuition than on the problem solving. So I would say that this process of doing the class, why I like to start with the problem sets, is that I like to go through and see what is required to solve these problems. Now, I mean, doing formulas like this may not seem to be that related to intuition, but as you can see, each of these problem sets, I kind of articulate some of the concepts that I think I have already. So when we were talking about some of the stuff with waves, when we were talking about some of the stuff with Fourier transform, with probability, with Dirac deltas, operators, what does eigenfunctions mean, eigenstates, these are important mathematical concepts that I think are going to be relevant in these problem sets that I already have some understanding of. And so the goal is going to be to apply them in this new domain, take stuff that I've learned previously, apply it in this new domain, and to really get an intuition. Because what I'd like to be able to do is, really have okay, well, this is obvious why this works the way it does. And that should really help with doing the problem sets, particularly the ones that don't require, pages and pages of calculus and algebra and tricky, tricks to try to solve the problem. Like as long as it's, not too heavy on that, it should be fairly easy. And I'm looking at the problem sets. Right now, the problem sets look more conceptual. I don't know that for sure, but they look more conceptual. They don't look like, I have to be really tricky. I have to have all these identities and proofs and crazy calculus to be able to solve them. I mean, sometimes they do. So I haven't looked at the solution sets yet. Because I don't have tons of materials, I didn't look at the solutions. Now, an easy way you could do this if you have tons of material is to look at all the solutions and be like, well, was I actually right? Is that actually how you solve it? And then that can trim off a lot of time. But I'm not doing that right now, partially just because I kind of want to go through the class and then try these problem sets again and see if I can actually solve them without looking at the answers. So what do we have to do left? So I've now reviewed 4-ish, kind of 3. The last one I didn't really review everything of the problem sets, of which there are 10 for this particular class. I want to go through 24 lectures. That means I'm a little slow right now. So I think for the rest of today, I'm probably just going to be doing lectures and notes. I'm not going to be doing any problem sets. I think if I want to get to, let me just go back to the calendar here. If I want to get to it, I think I want to try to get through maybe, I don't want to go too far without doing practice, but looking at these problem sets, I think I'd probably be safe if I got to about lecture 10. So if I get to 10 lectures, they're about an hour and a half each. I can probably do maybe 2 with some recap and some, debriefing after each of them. I can do 2 per studying session because I'm doing these 3-hour chunks. So you can do probably 4 a day. 4 a day with maybe another 2 today. I should be able to get through the first 10 lectures by Wednesday. And so Thursday, Friday, I think I'd like to start working on these problem sets. And then if I can get done problem set 5, I think, what do I want to look at? I think what I'll do is I'll get to lecture 10, work on problem sets Thursday and Friday, and then get kind of a feeling of how difficult this is and whether I need to go back a class and whether I need to do anything else. And then otherwise just go jump into the next week and then try to do the remaining 14 lectures in the second week, and then jump back into the problem sets. And then I should be able to get everything done. Should be able to get all the lectures done by the 15th and start working on the problem sets. And I will have some problem, like I won't do what I did in the MIT challenge where I just go straight through the entire class and then go problem sets, because I think that's probably going to cause issues. Now, I do have an hour and 15, that's 2.5 hours. So I have about 15 minutes on each, assuming I'm not going higher speed with anything, which I probably will go higher speed. So I might be able to squeeze some Feynman techniques in between the classes, or at least just kind of an overall, like, here's what we learned in the class, active recall, recap, which will hopefully keep everything in place. I do believe there's clicker assignments, which I might want to even pause the lecture in the class so that I can work it out if I'm slower than the students in the class, which might happen. So I think that's pretty good. We've got about half an hour left. I can start a new lecture right now, but I'm going to have to pause it halfway through. So maybe I'll just go to the live dashboard. Does anyone have any questions about what I've been doing? And I'll just kind of look at some of the stuff. Looks like lots of people are chatting in the chat, but they're chatting with each other, not so much with me. So does anyone have any questions about what I'm doing? And so one person was saying, what's the purpose of going over problem sets first? So as I said, part of it is just to get a sense of where I'm at. The other reason is that I like to do the problem sets first because it cues, okay, this is how I have to pay attention to it. So one of the things I like to talk about is that a lot of people view learning as a static kind of activity. So meaning that when you're learning something, it's about having knowledge in your brain. And I don't think that that view of learning is actually accurate. Really what you should think about when you're learning is you're actually learning both a context and a response. And this is kind of harder to visualize for more abstract and theoretical subjects like math, but essentially it's not really the case that I'm learning quantum physics. Rather, I'm learning quantum physics as it applies to particular situations. And so in some of those situations, that's going to be conceptualizing something, like so I can have a visual intuition of what's going on. But in this class in particular, a lot of that is doing math. A lot of that is understanding these concepts at a level where I can solve certain types of problems. And so given that that's why I'm doing it, I think it's important to look at it in a way that you are first looking at what's the usage situation so that you are making that pairing more explicit. I mean, in the lectures, they're going to show how they're using these problems, so it's not a huge issue to do the lectures first. But I like to kind of know what I'm getting into. What is the things that I don't understand? And I already articulated in these problem sets a bunch of things that I do understand and a bunch of things that I don't understand. And I'm going to be using that as sort of my roadmap for, okay, what are the blanks that need to be filled in this whole process? So I think I think we've got, I don't know if I have any other questions that people wanted to ask me. So someone was asking, what are the prerequisites for this class? Prerequisites would be calculus, multivariable calculus, differential equations. I think mostly to get to Fourier transform, though. I don't think we're going to be solving a lot of ordinary or partial differential equations. I haven't seen any so far. So it's mostly Fourier transform, which is, they usually do that in that class, but I don't think it would be necessary to do it all the way. You definitely need 801, 802 physics. 803 is a requirement. It seems to be showing up in the first assignment. It's asking a lot of stuff about classical waves, which I haven't studied that, so I'm missing that prerequisite too. So we'll see. So yeah, if anyone has any questions, you can ask in the chat. I'll just wait a couple minutes, just take a quick breather after this, and then I think I'm going to jump in and just start doing the first lecture because, yeah, time, better not waste time. All right, well, on that note, I think I am going to switch over now and look at doing one of these lectures. Now, I've already got it queued up, and so what I'm going to do is just open a new thing. And the way I've done it is I'm going to be watching the video with you guys. I don't know how well the video quality is going to be. Now, I was doing some tests last week about this, and I found that me watching a video sometimes causes lags. Now, I'll say a couple things about that. One, it mostly causes lags in the video, not the audio, because that's coming through the mic and that doesn't have to buffer. So you should be able to hear the classes okay. It just might be a little harder to follow stuff on the chalkboard. If you are following this and you're really enjoying it and you want to watch what I'm doing, I think that the video quality is going to be better in the after YouTube has processed it. So I was watching the videos live and they're a bit choppier than they are when you're watching this video as a static video. So if you're watching the recap of this, it should be a bit easier. Alternatively, of course, these videos are freely available on the website that I posted in the chat recently. So you're also free to just, mute me and pop up your own version of the chat or this kind of thing, and you can walk along. Or you can mute your audio and watch your video, which is not going to have any of these potential latency issues, and go through it. So let's go through and watch this video. And yeah, I'm excited. And now we're getting into the lectures. So let's jump forward. Oh, hold on a sec. All right, and I'm going to send to live now. So I'm just going to this up a little bit. All right.
And under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Hi, everyone. Welcome to 804 for spring 2013. This is the fourth and presumably final time that I will be teaching this class, so I'm pretty excited about it.
All right.
So my name is Alan Adams.
So let's just skip ahead of all this preamble.
I study string theory and its applications to gravity, quantum gravity, and matter physics. Quantum mechanics. This is quantum mechanics. Quantum mechanics is my daily language. Quantum mechanics is my old friend. I met quantum mechanics 20 years ago. It's really how it's so old friend. It's also my most powerful tool. So I'm, pretty excited about it. Our presentation instructors are Arts Enoch, yay! And Matt Evans, yay! Okay, Matt's new to the department, so welcome him. Hi. So he just started his 5 minutes, which is pretty awesome. And our TA is Paolo Glorioso. Paolo, you here? Hey! Okay, so University of Sentinel complaints too. So just out of curiosity, how many of y'all are course 8? Oh, awesome. How many of y'all are, 18? Solid. 6? Excellent. 9? No one? Yeah, this is the first year I've had anyone. Let's talk about students. So 2 practical things to know. First thing is everything that we put out will be on the Stellar website. Lecture notes, homeworks, exams, everything's going to be on through Stellar, including your grades. The second thing is that, as you may notice, there are less than usual on Ring Link, and when you sign up, we're going to be video meeting, of course, for the lectures.
So I'm going really fast just because he's just talking to the class about stuff that isn't really relevant to the material. So I'm just going to slow it down once we get to the actual material.
So the goal of Data Force is to learn quantum mechanics. By learn quantum mechanics, I don't mean learn how to do calculations, although that's an important and critical thing. I mean learn some intuition. I want you to develop some intuition for quantum phenomena. Now,
Intuition, yay.
Is being a hard topic. It is not a super hard topic. It does, however, require, so in particular, everyone in this room are totally positive can learn quantum mechanics. It does require concerted effort. It's not a trivial topic, okay? And in order to really develop a good intuition, the essential thing is to solve problems. So the way you develop a good intuition is by solving problems and by dealing with new situations, new contexts, new regimes, which is what we're going to do in Data Force. It's essential that you work hard on problem sets. So your job is to devote yourself to the problem sets. My job is to convince you at the end of every lecture that the most interesting thing you could possibly do when you leave is the problem set. So you decide who has the harder job. So the workload is not so bad. We have problem sets due that are due in the physics box in the usual places by lecture by 11 a.m. sharp on Tuesdays, okay, every week. Late work, no, not so much. But we will drop one problem set to make up for unanticipated events. We'll return the graded problem set a week later in recitation. Should be easy. I strongly encourage you to collaborate with other students on your problem sets. You will learn more. They will learn more. It will be more efficient. Work together. However, write up your problems to yourself. Okay, that's the best way for you to develop and test your understanding. There will be 2 midterms, dates to be announced, and 1 final. If you could have multiple, that would be a little exciting. We're going to use clickers, and clickers will be required. We're not going to take attendance, but they will give a small contribution to your overall grade, and we'll use them most importantly for non-graded but just participation, concept questions, and the occasional in-class quiz to probe your knowledge. This is mostly so that you have a real-time measure of your own conceptual understanding of the material. Okay, this has been enormously valuable. And something I want to say just right off is that the way I've organized this class is not so much based on how the classes I was taught. It's based to the degree possible on empirical lessons about what works in teaching. Okay, what actually makes you learn better. And clickers are an excellent example of that. So this is mostly a standard lecture course, but there will be clickers used. So by next week, I need you all to have clickers, and I need you all to register them on the TSU website. There are, I haven't chosen a specific textbook, and this is discussed on the Stellar webpage. There are a set of textbooks, 4 textbooks that I strongly recommend, and a set of others that are nice references. The reason for this is twofold. First off, there are kind of 2 languages that are canonically used for quantum mechanics. One is called wave mechanics, and the language, mathematical language, is partial differential equations. The other is matrix mechanics, they have big names, and the language there is linear algebra. And different books emphasize different aspects and use different languages. And they also try to aim at different problems. Some books are aimed towards people who are interested in material science, some books are aimed towards people who are interested in philosophy, and depending on what you want, get the book that's suited to you. Okay, and every week I'll be providing with your problem sets readings from each of the recommended tests. So what I really encourage you to do is find a group of people to work with every week, and make sure that you've got all the books covered. This will give you as much access to the text as possible.
So hopefully not having the textbook's not going to be an issue.
So finally, I guess the last thing to say is if this stuff were totally trivial, you wouldn't need to be here. So ask questions. If you're confused about something, lots of other people in class are also going to be confused. And if I'm not answering your question because I'm asking, then no one's getting the point, right? So ask questions. Don't hesitate to interrupt. Just raise your hand and I'll do my best to call you. And this is true both in lecture, also during office hours, and recitation. Ask questions. I promise there's no such thing as a terrible question. Someone else will also be confused. So it's very valuable to me and everyone else. Okay. So before I get going on the actual physics content of the class, are there any other practical questions? Yeah. Latest policy. No late work is accepted whatsoever. There it is. So the deal is, given that every once in a while, you're going to be walking to school and your leg is going to fall off or a dog's going to jump out and your person's going to see whatever. Things happen. So we will drop your lowest problem set score without any questions, right? At the end of the semester, we'll just drop the lowest score, and if you turn them all in...
He's still talking about stuff. I'm going to speed him up.
On the other hand, if you know, like, next week, I'm going to get hacked out of this world, it's going to be horrible. I want to work on my problem set. Could we work this out? So if you don't have time, come to us. We need to do that well ahead of time. Okay? Yeah? I don't know. I don't think so. I think it's going to happen at the end of the semester. Yeah, okay, so no, it'll later on this year. Other question. Yeah. Oh, that's an interesting question. I don't have to put my head, but if you send me an email, I'll preserve it. I do know several other lecture series that I like very much, but I don't know if they're available on YouTube or publicly. So send me an email, I'll check. Yeah. Reading assignments on the problem set every week will be listed. There will be equivalent reading from every textbook, and if there's something missing, like if no textbook covers something, I'll post a separate reading. Every once in a while, I'll post auxiliary readings, and that'll be available on the Stutter website. So, for example, on your concept, which is first one is posted, will be available immediately after lecture on the Stutter website. There are 3 papers that refers to, or 2, and they're posted on the Stutter website and linked from the website. Others. Okay, so the first lecture, the content of the physics of the first lecture is relatively standalone. It's going to be an introduction to a basic idea that is going to haunt, plague, and charm us through the rest of the semester. Okay. The logic of this lecture is based on a very beautiful discussion in the first few chapters of the book by David Albert called Quantum Mechanics and Experience. It's a book for philosophers, but the first few chapters are really lovely introduction at a non-technical level, and I encourage you to take a look at it. It's very lovely. But it's, to be sure, straight up physics.
Okay. Let's go back up to ordinary speed just to start watching it. We might speed up later.
Today, I want to describe to you a particular set of experiments. Now, to my mind, these are the most unsettling experiments ever done. These experiments involve electrons. They have been performed, and the results, as I will describe them, are true. I'm going to focus on 2 properties of electrons. I will call them color and hardness. Okay. And these are not the technical names. We'll learn the technical names for these properties later on in the semester, but to avoid distracting you by preconceived notions of what these things mean, I'm going to use ambiguous labels, color and hardness. And the empirical fact is that every electron that's ever been observed is either black or white and no other color. We've never seen a blue electron. There are no green electrons. No one has ever found a fluorescent electron. They're either black or they are white. It is a binary property. Secondly, their hardness is either hard or soft. They are never squishy. No one's ever found one that dribbles. They are either hard or they are soft. Binary properties. Okay? Now, what I mean by this is that it is possible to build a device which measures the color and the hardness. In particular, it is possible to build a box, which I will call a color box, that measures the color. And the way it works is this. It has 3 apertures, an in port and 2 out ports, one which sends out black electrons and one which sends out white electrons. Okay. And the utility of this box is that the color can be inferred from the position. If you find the particle, the electron over here, it is a white electron. If you find the electron here, it's a black electron. Cool? Similarly, you can build a hardness box, which again has 3 apertures, an in port, and hard electrons come out this port, and soft electrons come out this port. Okay. Now, if you want, you're free to imagine that these boxes are built by putting, a monkey inside, and you send in an electron, and the monkey, with the ears, looks at the electron and says, it's a hard electron that sends it out one way, or it's a soft electron that sends out the other. Do not matter. In particular, later in the semester, I will describe in considerable detail the workings inside this apparatus. And here's something I want to emphasize to you. It can be built in principle using monkeys, hyper-intelligent monkeys that can see electrons. It can also be built using magnets and silver atoms. It can be done with neutrons. It can be done with all sorts of different technologies, and they all give precisely the same results as I'm about to describe. Okay? They all give precisely the same results. So it does not matter what's inside, but if you want a little idea, you can imagine putting a monkey inside, a hyper-intelligent monkey. That sounds good. So I'm going to call, So a key property of these hardness boxes and color boxes is that they are repeatable. Here's what I mean by that. If I send in an electron and I find that it comes out of a color box black, and then I send it in again, then if I send it into another color box, it comes out black again. So in diagrams, if I send in some random electron to a color box, and I discover that it comes out, let's say, the white aperture, and so just and I keep going to come out the white aperture and send it into a color box again, then with 100% confidence, 100% of the time, the electron coming out of the white where it's incident on the color box will come out the white aperture again, and 0% of the time will come out the black aperture. So this is a persistent property. You notice that it's white. You measure again, it's still white. Do it a little bit later, it's still white. Okay? It's a persistent problem. Ditto the hardness. If I send in a bunch of electrons into hardness box, here's an important thing. Well, I send them into a hardness box, and I take out the ones that come out soft. And I send them again into a hardness box, and they come out soft. They will come out soft with 100% confidence, 100% of the time. Never do they come out the hard average. Okay. Any questions at this point? So here's an actual question. Might the color and the hardness of an electron be related? And more precisely, might they be correlated? Might knowing the color infer something about the hardness? So for example, so being male and being a bachelor are correlated properties because if you're male, you don't know if you're a bachelor or not, but if you're a bachelor, you're a male. That's the definition of the word. So is it possible that color and hardness is really correlated? So, I don't know, there are lots of things like wearing a red shirt and beating down to the surface and making it back to the Enterprise later after the awakening return. Correlated, right? Negatively, but correlated. So the question is, suppose we know that an electron is white. Does that determine a hardness? So we can answer this question by using our boxes. Yeah. So here's what I'm going to do. I'm going to take some random sets of electrons, random, and I'm going to send them into a color box. And I'm going to take the electrons that come off the white aperture. And here's a useful fact. When I say random material operationally, what I mean, I take some piece of material, I scrape it, I pull off some electrons, and they're totally randomly chosen from the material, and I send them in. If I send a random pile of electrons into a color box, useful thing to know, they come out about half and half. It's just some random circles, some of them white, some of them come out black. Suppose I send some random collection of electrons into a color box, and I take those which come out the white aperture. And I want to know does white determine hardness, so I can do that, check, by then sending these white electrons into a hardness box and seeing what comes out. And what we find is that 50% of those electrons incident on the hardness box come out hard, and 50% come out soft. Okay? And ditto if we reverse this, if we take hardness, we take, for example, a soft electron and send it into a color box, we can get 50-50. Okay. So if you take a white electron and send it in a hardness box, you're at even odds. You're at chance as to whether it's going to come out hard or soft. And similarly, if you send a soft electron into a color box, even odds it's going to come out black or white. Okay. So knowing the hardness does not give you any information about the color, and knowing the color does not give you any information about the hardness. Cool. These are independent facts, independent properties. They're not correlated in this sense, in precisely this operational sense. Cool. Questions? Okay. So measuring the color gives 0 predictive power for the hardness, and measuring the hardness gives 0 predictive power for the color. And from that, I will say that these properties are uncorrelated. H, hardness, and color are, in this sense, uncorrelated. So, using these properties of the color and hardness boxes, I want to run a few more experiments. I want to prove these properties of color and hardness a little more. And in particular, knowing these results allows us to make predictions to predict the results for a set of very simple experiments. And what we're going to do for the next bit is we're going to run some simple experiments, and we're going to make predictions, and then those simple experiments are going to lead us to more complicated experiments. Well, let's make sure we understand the simple ones first. So, for example, let's take this last experiment, color hardness, and let's add a color box, one more motion. So, color, and we take those that come out the white aperture, and we send them into a hardness box, hard soft, and we take those electrons which come out the soft aperture, and now let's send these again into a color box. So it's easy to see what to predict. Black, white. So you can imagine a monkey inside this going, you look at it, you inspect, it comes out white. Here you can inspect, it comes out soft. And you send it into the color box. And what do you expect to happen? Well, let's think about the logic here. Anything reaching the hardness box must have been measured to be white. And we just did the experiment that if you send a white electron into a hardness box, 50% of the time it comes out a hard aperture, 50% of the time it comes out soft aperture. So now we take that 50% of electrons that comes out the soft aperture, which had previously been observed to be white and soft. Then we send them into a color box, and what happens? Well, since color is repeatable, the natural application is that, of course, it comes out white. So our prediction, natural prediction here, is that of those electrons that are incident on this color box, 100% should come out white, and 0% should come out black. That seems like reasonable? So let's just make sure that we're all agreeing. Sorry, let's vote. How many people think this is probably correct? Okay, good. How many people think this is probably wrong? Okay, good. That's reassuring. except you're all wrong, right? In fact, what happens is half of these electrons exit white, 50%, and 50% exit black. So let's think about what's going on here. This is really kind of troubling. We've said already that knowing the color doesn't predict the hardness. And yet, this electron, which was previously measured as being white, now when subsequently measured, sometimes it comes out white, sometimes it comes out black, 50% of the time. Okay? So that's surprising. What that tells you is you can't think of the electron as a little ball that has black and soft written on it. Right? You can't, because apparently that black and soft isn't a persistent thing, although it's persistent in the sense that once it's black, it stays black. So what's going on here? Now, I should emphasize that the same thing happens if I had changed these to if I had changed this to taking the black electrons and throwing in hardness and picking soft and then measure the color, or if I had used the hard electrons. Any of those combinations, any of these works would have given the same results, 50-50. It is not persistent in a sense. Apparently, the presence of a hardness box tampers with the color center. So it's not quite as trivial as that hyper-intelligent monkey, right? Something else is going on here. So this is suspicious. So here's the first natural move. The first natural move is, oh, look, surely there's some additional property of the electron that we just haven't measured yet that determines whether it comes out the second color box black or white. Right? There's got to be some property that determines this. And so people have spent a tremendous amount of time and energy looking at these initial electrons and looking with great care to see whether there's any sort of feature of these incident electrons which determines which port they come out of. And the shocker is, no one's ever found such a property. No one has ever found a property which determines which port it comes out of. As far as we can tell, it is completely random. Those that flip and those that don't are indistinguishable at the beginning. And let me just emphasize, if anyone found such a, it's not like we're not looking, right? If anyone found such a property, fame, notoriety, subverting quantum mechanics, Nobel Prize, people have looked, and there is none that anyone could be able to find. And as we'll see later on, using Bell's inequality, we must nail that such things don't exist. Such a fact feature. But this tells us something really disturbing. This tells us, and this is the first real shocker, that there is something intrinsically unpredictable, non-deterministic, and random about physical processes that we observe in a laboratory. There's no way to determine a priori whether it will come out black or white from the second box. Probability in this experiment is forced upon us by observations. Okay, well, there's another way to come at this. You could say, look, you ran this experiment, that's fine, but look, I've met the guy who built these boxes, and look, he's just some guy, right? And he just didn't do a very good job, right? The boxes are just badly built. So here's the way to defeat that argument. No, we built these things out of different materials, using different technologies, using electrons, using neutrons, using buckyballs, C60, seriously? No. Okay? We've done this experiment, and this property does not change. It is persistent. And the thing that's most upsetting to me is that not only do we get the same results independent of what objects we use to run the experiment, we cannot change the probability away from 50-50 at all. To within experimental tolerances, we cannot change, no matter how we build the boxes, we cannot change probability by part 100. Okay? 50-50. And to anyone who grew up with determinism for Newton, this should hurt. Right? This should feel wrong. But it's a property of the real world, and our job is going to be to deal with it. Okay? Rather, your job is going to be to deal with it, because I went through this already. So, okay? So here's a curious consequence. Oh, any questions before I cruise? Okay, so here's a curious consequence of this series of experiments. Here's something you can't do. Are you guys old enough where you can't do this on television? Oh, this is so sad. Okay, so here's something you can't do. We cannot build, it is impossible to build a reliable color and hardness box. We built a box that tells you what color it is. We built a box that tells you what hardness it is. But we cannot build a meaningful box that tells you what color and hardness an electron is. So if you think of what would this magical box be, it would have 4 parts. And this port would say, well, one is white and hard, and one is white and soft, and one is black and hard, and one is black and soft. So you can imagine how you might try to build a color and hardness box. So for example, here's something you might imagine. Take our incident electrons and first send them into a color box. Okay? And take those white electrons, take the white electrons and send them into a hardness box. And take those electrons, and this is going to be white and hard, and this is going to be white and soft. Okay, and similarly send these black electrons into the hardness box. And here's hard and black, and here's soft and black. Okay. Pretty cool that? So this seems to do the thing I wanted. It measures both the hardness and the color. What's the problem with it? Yeah, exactly. So the color is not persistent. So you tell me this is a soft and black electron, right? You told me it's here's the box. But if I put a color box here, that's the experiment we just ran. And what happens? Does this come out black? No, this is a crappy source of black electrons. It's 50-50 black and white. Right? So this box can't be built. And the reason, and I want to emphasize this, the reason we cannot build this box is not because our experiments are crude. And it's not because I can't build things, although that's true. I was banned from the lab one day after joining it, actually. So I really can't build, but other people can, okay? And that's not why. We can't because there's something much more fundamental, something deeper, something in principle, which is encoded in this awesome experiment, okay? This can't be done. It does not mean anything as a consequence. It does not mean anything to say this electron is white and hard. Because if you tell me it's white hard, and I measure white, well, I know it's hard is going to come out 50-50. It does not mean anything. So this is an important idea. This is an idea which is enshrined in physics with a term which comes with capital letters, the uncertainty principle. And the uncertainty principle says basically that, look, there are some observable, measurable properties of a system which are incompatible with each other in precisely this way. Incompatible with each other in the sense that not that you can't ask, not that you can't know, because you can't know whether it's hard and soft simultaneously. Deeper, it is not hard and white simultaneously. It cannot be. It does not mean anything to say it is hard and soft, hard and white simultaneously. That is uncertainty. And again, uncertainty is an idea we are going to come back to over and over in the class. But every time you think about it, this should be the first place you start for the next few weeks. Yeah. Questions? No questions? Okay, so at this point, it's really tempting to think, yeah, okay, this is just, this is just about the hardness and the color of the letter.
Okay, I'm going to pause it right there. I'm just going to go back to my main screen here. So it's almost 11 o'clock my time. As I said, there's a bit of a 1 or 2 minute delay, so you might be getting this a little later. But I'm going to try to stick to this schedule as much as possible just because I've got a lot of other work to do and other things that are going to be happening. And I think it'll be better to be consistent than if I'm randomly going late or early some other times. So what did we do in this little session? Well, it was a little slow to start because I spent a lot of time explaining why I'm doing it, what I'm doing it this way. I think in the future sessions, I'm just going to jump right in. I'm not going to have the long preamble. But we went through the first 4 problem sets. It looks like there's quite a bit that I already kind of understand. So that's good. I mean, it's always hard when you're reading it and it's just, whoa, I don't understand any of the words that this is saying. I don't understand anything that's being said here, because that means you got to learn a lot of new things. Now, some of it is that like there were terms that they were being used. There was these eigenstates, which I wasn't sure what an eigenstate was, commutator. There was, a lot of Greek letters that maybe I've been mispronouncing on this feed. There's a lot of those things. And I think they will get resolved in there because sometimes you're just missing a terminology or the concept's not that difficult. You've just never been taught it before. And that's why you need to do lectures. That's why you need to read a book to learn these kind of concepts at all. But I do think it's good to start with the problem set because it gives me kind of a sense of what I'm looking for. Now, we also started covering about the first 20 minutes of the lecture. I did most of it at 1.5 speed. I think for a lecture like this, where there's not a lot of math happening, it's easy to go a bit faster because I can understand what he's saying when he's talking. Al Adams, great lecturer. As I said, I've already watched a few of these videos already. Really enthusiastic. This is what I loved about the MIT lectures when I was doing the MIT challenge. Just like world-class instructors and professors. So they're really entertaining to watch. I know that they can be kind of a little bit difficult mentally, so they're not the same as, a dumb YouTube video, but they are something that is just, fascinating. And he really brings that passion, you can tell, in this just first class where we're talking about the things that interest me about quantum physics. Like, this stuff is kind of crazy. And so we're just sort of at the kind of laying the kind of preamble, at least in the lectures. I'm going to be back later this afternoon, and I'm going to try to chew through some more lectures. If I can keep up the 1.5 times speed, we might be even done a little bit before the end of Wednesday, in which case that's great because then I can get more time on the problem set, because that's going to be where things are tricky because it's easy to follow a lecture, but if you actually have to solve problems and you're missing some mathematical techniques or concepts, or I've forgotten them from past classes, there might be a little bit more relearning there. I might have to go back to the books and might have to do a bit of that stuff. So I'm going to be around for just 2 more minutes. If anyone has any questions about what I'm doing or this kind of thing, just feel free to mention it in the chat, and I can I can try to respond to it. So again, I'm not quite sure how this live stream thing is working. This is my first time ever doing any kind of live stream. I mean, I've done webinars before, but those are different because I'm giving a speech. I'm not actually trying to do something while I'm on camera. So we'll see how this goes. I mean, I think it would be very interesting to see if anyone wants to participate, who wants to help out with some of the problem sets or wants to see what's going on. But obviously, I know this is not the easiest class. It would have been nice if I could have tackled a subject that everyone had the right prerequisites for it, but I've done enough classes now that now I actually, if I'm going to do a class that I have to showcase what it's like to actually learn it as opposed to just doing it because it's easy, I have to pick classes that are now a little bit more advanced and a little bit harder. So at the very least, you can follow the lectures, you can listen along with me. And if you are interested in this subject, I'm hoping that, this can give a little bit of a guidance on how to learn it. And I think this applies for a lot more than just quantum mechanics. Pretty much any kind of technical or math class, you can use a similar sort of approach. It's going to be a little different for classes where, they're less mathematical. I would take slightly different approaches, but I'm hoping to just use this as sort of a benchmark and explain why I'm doing things. If you're ever unsure of why I'm doing something or what my approach is, or this kind of thing, you can say it in the chat. I'm not always paying attention to the chat in the moment, just because I can't keep my eyes on everything at once. But I'm going to try to take little breaks to kind of pause, say what's happening, what I'm trying to do, what I'm thinking, and that. So thank you for joining me on this first day. This is exciting. I'm going to be doing this all month, and hopefully we're going to have a really good understanding of quantum mechanics. And maybe after the month is done, I can put together a little kind of explaining what I've learned. We'll see how that goes. See if anyone has any interest in reading something like that. So thanks for everyone who's been watching me on this thing. And if you're watching the recording of this, if you're watching it after I've done it live, then I'm hoping that you'll stay in touch and keep watching the progress for the project. Thanks.